Today, this is final fourth day of GHG-3 workshop. And last 3 days, we have done very interesting talks as well as discussions and these things. So today we have lined up very important talks whole day. So in order to that, the first talk is by Dr. C.G. Kumar. So Dr. C.G. Kumar is a well-known personality in carbon cycle field now, but I will just give a brief research overview and then I will tell about him. So Dr. C.G. Kumar is now scientist SF at SPL VSSC at Trivandrum, and he has done his BSc Physics in 91, MSc Space Physics 94 from Andhra University, and then he did his PhD in Atmospheric Sciences in 2003 from Kochi University of Science and Technology, and then he became a scientist at SPL. So his research interest mainly lies in understanding the role of biospheric and anthropogenic activities on the carbon cycle using inverse modeling by combining atmospheric greenhouse gas measurement and numerical models, and monitoring and modeling of climate in the Earth system on a multitude of temporal and spatial scale using observation data and numerical models. So he has many publications on his credit. Few of publications, recent one where we have shown the carbon cycle observation network over India. That paper is really very benchmark paper. And he has many other publications, and he guided a few theses also in the field of carbon cycle. So I request Dr. C.G. Kumar to please give his lecture here so that we all can be benefited. Thank you.
Thank you, Yogesh. Nice introduction. Good morning, all. I'll be covering talks about this. Our work about the regional estimation of the carbon flux over India. We have contributors are there, so from SPL side as well as ATM and NARL. So I'll be just, even though we have seen this observational features of last 2-3 days, but still I want a continuation. I'll just show the GSAT observations and AAR started observations over Indian region for the years. This is the average picture on 2009 to 2016. So the first panel shows the GSAT L3 product, and the second panel is AAR satellite data. From you can see that from the GOSAT, we can see there is large seasonal variabilities in the carbon dioxide. For example, winter time and 3 months on time there is an enhancement in the carbon dioxide, and then there is the concentration is decreasing over monsoon time, and then again it is. But in the case of AARS, the seasonal cycle is not that much visible, not clearly. Why? Because this AARS mainly sees the CO2 from some upper troposphere, so may not represent the surface as well. And another important point, we can see that during the monsoon season there is a large gap in the data over in the region. It's mainly because of the cloud coverage during monsoon time, because mostly the sensors are in infrared sensors, so it may not be able to penetrate the cloud region. So there is a large gap that over in the region during the monsoon season. That is one of the limitations of the current satellite observations. We try to compare this satellite data with the available data flask of measurements from the Senegal and Cape Rama. So this we have compared with the GOSAT L3 and L4, and then carbon tracker data with Senegal is the first figure, and the second one is the Cape Rama. So you can see that the L3 and the flask, the difference is comparatively large. As years progress, the difference increases also. The Senegal data is giving a sharp enhancement during the years, but L3 product, GOSAT L3 may not be able to catch that enhancement. But L4, they assimilate some data or the regional data, so L4 is slightly better than the L3 in comparison with the flask. And first few years, because carbon tracker is almost agreeable with the past measurements. But later, the carbon tracker also shows there is a difference is a little bit higher. But in the case of Capriama, except the L3, the carbon tracker and L4 products are almost comparable with the flask observation of the Capriama. But L3 is a large difference is there. One reason for this mismatch is that because satellites is in a large area and maybe the averaging representing over a large area may not be able to represent a point source, and so this discrepancy in the satellite data observations and the ground observation is indicating that we require more observations so that these observations can be fed to the satellite retrieval thing, and we can go maybe the L4 products like that, we can derive products, we can improve quality. So we need to strengthen our ground observation. So question is that where we will put observation. If you put observations over a particular region, whether it is able to represent the Indian emissions, that is the one question we are addressed. So today's my topic talk will be covering like 3 areas. One is that first we talk about the network design, because where we need to put observational stations to get Indian emissions, and followed by I will be a little bit talking about the carbon dioxide flux estimation using Bayesian inversion model as well as methane inversion. So these 2 works are it's not well matured because we are trying to do more corrections, and actually it is a learning process for us for estimation, regional estimations. But this first work is already published in the atmospheric environment. So in the case of observational network, so there are some questions, some problems whether we are putting an observation or mostly we put observations based on our logistical availability, because suppose we are working in some in a particular lab nearby place, we try to choose the observation. So it may be used for this understand the seasonal or annual variabilities of CO2 over that region, or some study the local influence of that from the any sources are there or things are there. So the concentration variability, how this sourcing variability is affecting the local influence. But we need to ask 2-3 questions before setting up an observational station. So whether this measurement taken in this particular location will add to knowledge to the existing knowledge biochemical system, or whether the proposed network station, measurement station, can effectively reduce the uncertainty in the estimation of the source sensing of carbon dioxide or the particular region. So these are the 2 questions mainly we have to address putting up a measurement station. So there are some methodologies proposed by the literature, is available in the literature. So one is that synthesis inversion, that uses the atmospheric transport model simulations and the prior information of source strength along the uncertainty can be used to design an optimal network for the CO2 observation for a region. Another one is that it is a simulated annealing, but it is mainly used by the seismological network, seismological network. So it resembles the annealing of the crystal lattice, but the Rainer, it's proposed it can be used for CO2 observation network also. So there is another method called incremental optimization proposed by Patra and Shamil. So this is based on the Bayesian inversion modeling and global transport model. So we use this selected this incremental optimization method by the Patra and Shamil because it is computationally easy and methodology also comparatively easier for us other 2 methodologies. So this incremental optimization mainly is try to reduce the uncertainty of the posterior uncertainty this is the equation we are writing. Uncertainty reduction can be calculated from the covariance of the posterior uncertainty and the covariance of the prior uncertainty. So this covariance of the posterior uncertainty can be optimized from the Bayesian inversion. Bayesian inversion, again, for the youngsters, keep the slides. So Bayesian inversion, mainly we are using minimizing the cost function instead of the equation. So this is the cost function where that x is the surface plexus, unknown surface plexus, and xb is the prior plexus, and y0 is the atmospheric observation, and from this prior flux and that H is the transfer sensitivity. From the prior flux and transfer sensitivity, we can compute the model concentration, and here R is the observational uncertainty and B is the uncertainty of the prior fluxes. So by minimizing the cost function, we can get the posterior surplus flux by using these equations. And if you take the second derivative of the cost function, we will get another quantity called posterior uncertainty. So posterior uncertainty can be calculated from this transport sensitivity and observation uncertainty and prior flux uncertainty. We need not require in that observation for any observation for computing the posterior uncertainty. So this posterior uncertainty with the prior uncertainty, we can compute the uncertainty reduction, and with this uncertainty reduction, we can the incremental optimization method, we can design a network optimization over the region. So what we have done over the Indian region is that in this grid you can see that there is India over the Indian landmass. We regridded with the 2 into 2 regridded, we 2 degree into 2 degree grid we construct, and each grid we assume that it's a potential of a station, because it can be a station, representatives of a station. So there are 73 grids are there. So there are some grids which is shaded. So shaded grid is actually represents the observations, current observations available in the literature. So for example, this is the this grid representing that Pondicherry observation, and this grid is for Kodaikanal station, and this is for the Cape Rama and Sinagat and Mount Abu and Sharnagar, and because it is representing Sagar at that ATM was proposing, then this is our Sundarban and Karakpur, and so this 70 is representing the Kalne observation. So what we have done is that we use the flex path model. It is run by our meteorology used from the CFSR, ends of CFSR forecast system meteorology, and then the flex path model we configured with the resolution of 0.5 to 0.5 degree, and from the each grid we release the particle, almost 1 million particle we released from the every 7th, every 7th, 14th and 21st and 28th day of each month during the year 2012 to 2016. The 5 years we have simulated this flex path simulations. So total 240 simulations over a particular grid. So like that, for the entire grid, if you compute almost more than 17,000 ensemble simulation we are done. So it's a very strong database of the transport sensitivity, and then we use for example, you can see that transport. This is a seasonal mean of the transport sensitivity. If suppose for a station or Sinagat, if you look in that, because since Indian region is mainly dominated by the seasonal changes, because we know that summertime is the monsoon. Once the monsoon establishes, the southwesterly wind flow is dominating over the Indian region. So we can see that the transport also mainly from the Indian Ocean region, southern Indian Ocean region, and it follows. It's almost follows the monsoon low-level jet. So whereas in the other seasons, for example, the winter post-monsoon season, the transport is mainly from the northeast. The station Senegal is mainly from the northeastern region, and even winter time also it is like that. The north and eastern regional is mainly transport concentration, but the pre-monsoon region, it's mainly from the northwest region, the Senegal transport is there. So what we are doing with all the transport sensitivity, we average seasonal base for the winter time, pre-monsoons, monsoon, and post-monsoon season. So correspondingly, we are also average the flux uncertainties. So we repair the flux uncertainty. The flux uncertainty we are usually is the biosphere flux from the CASA and ODIAC fossil fuel. So this is a seasonal representative of the flux over the 4 seasons. So the observational uncertainty we have taken as a 2 ppm, which combines both the observational error as well as the model error. So initially what we have done is with this transport sensitivity and the uncertainty of prior and observation, we have tried to rank the existing stations. So the existing station we tried to rank for each seasons. So with incremental optimization section method. So in the, all the seasons, you can see that the Kharagpur is ranked first, but the Kharagpur rank. How we get the first rank station is that this is the station which has the maximum uncertainty over all the stations. So uncertainty reduction over that. So the Kharagpur station having winter time it has almost 8% uncertainty reductions, and pre-monsoon it is 6%, almost 6%, and monsoon season it is about 10%, and post-monsoon is around 12% uncertainty reductions. So then we add another stations. One by one we added which are reducing the uncertainty. Second most like that we added. Then so this is the ranking for the stations for the winter seasons, and the Hanle which is over the top of our northern Himalaya, and it is the northern side of India, which mainly as a background station, it is lesser representing the Indian land, because almost all seasons it comes as lower rank region. And for this monsoon season, Cape Rama also is the lowest rank, because the monsoon season, Cape Rama is the western coast of the Indian peninsula India. So it mainly sees the flow from the Indian Ocean only, not from the land region. So for overall, the existing stations could reduce the 30% uncertainty reduction during the winter time, and so almost 18% during the pre-monsoon, and 25% on monsoon season, and around 36% during the post-monsoon seasons. So we can add more stations to reduce more uncertainty, but on limitations with adding more stations to the existing network is that it is already having a bias, because even though some stations is not qualifying well, for example, for the Hanle station from the Senegal to Hanle, the uncertainty reduction is almost 0.04% only. So it will be a liability if you are adding more stations to this network. So what we have done is that we tried to propose a new network without considering any of the stations. We included all the 73 stations, and we tried to find out which one has the maximum uncertainty reductions can be obtained. So based on this new proposed stations, including all the stations as a new set, we could reduce the uncertainty up to almost close to 50%. Because only on winter time it is 46%, and pre-monsoon is almost 40%, and monsoon season is 47%, and post-monsoon it is more than 50% with this 12 station. If you include the 12 stations, we can reduce this that almost close to 50% reduction can be done. But this each seasons the stations representation is different. For example, some stations are common, but some stations it is not. It is only qualified for some particular seasons. For example, this Kharagpur station. Kharagpur station is stopped in the post-monsoon season, but it is winter season. It is ranked 4, but it is included almost all stations. But except the monsoon season. Monsoon season, there is a station near to the Kharagpur that qualified. It's 47 and 48. This number is almost in the eastern region only. So based on these new stations, we proposed a consolidated 17 stations because which one is common and we have common stations we avoided, and on annual basis we when they concluded that there is 17 stations can represent the Indian, can reduce the uncertainty almost 50% if you use these stations as a network observations. Most of the 3 stations is qualified in this network. One is that Kaprama, Pondicherry, and Kharagpur region. But this is a large region. When it is about, for example, this region, Shadnagar and this 15 is almost the same latitude only. So there are some closer regions stations we can also consider, but also we have just to see that this grid that we are proposing is the large area, that is 2 into 2 degree. So anywhere we can put that observations, but an important thing we have the more stations over the eastern part and the Indo-Gangetic plain and the southern state compared to the western region, because western region mostly the winter season and post-monsoon season, mostly the wind is coming from the north to eastern region. So the transport sensitivity is mainly concentrating on southern peninsula and north and eastern than the northwestern peninsula. So this is the network we are proposing as a optimal network for the carbon dioxide, and this work is published in Atmospheric Environment in 2019, and it's a part of the Nalini's thesis work. So next I'll be covering on this our regional inversion of the carbon dioxide CO2 measurements. So we try to use this observations and our transport metrics from the flex part to derive a posterior fluxes. So this is the schematic diagram of our inversion system. So our transport model is the flex path model, which is from the meteorology from the either NSUB or reanalysis. We can use that. So our transport flex path will give you the transport sensitivity. So if you multiply this transport sensitivity with the available prior emission fields, either biosphere or fossil fuel, all the emission fields we multiply, we can get the enhancement over the Indian region, or the region enhancement we can get. If you add the enhancement to the background of background mixing ratio, we can get the model mixing ratio. So from the model mixing ratio and the observation, we combine and we reduce the mismatch with the Bayesian optimization. We will get that, the posterior and flex. So here the notation is slightly different from the earlier my slide. So this is the schematic of our current regional inversion system, but we are using at present at SPL. So this here the enhancement is what we mean that this is a change in the flux during the simulation period, because 7 days transport. What is the change in the flux due to the transport over this region? So background yesterday, that is what we have discussed yesterday. Also how we can compute the background mixing ratios. At present we are computing the background mixing ratio from this reanalysis, CAMS reanalysis, or for carbon tracker. Both we are trying to use this back as a background mixing ratio. So the observations we have, you see, the present for CO2 we have taken the data. We have on Tumba observation, we have that CDRS observations, and then we have that Srinagar flash measurements. So these 2 observations we have done, and we tried to do the inversion in the period 2017 and 18. Here we have considered this observation uncertainty as 1 ppm. So the prior fluxes we have used is that biospheric flux from the CASA and Kodiak anthropogenic fossil fuel fluxes. So the CASA uncertainty, the CASA itself is giving the uncertainty that we have used, but for this fossil fuel we have that taken as the 12% as the value as the uncertainty. This is the purpose by Oda et al. In 2018, or the Indian region has proposed that almost 12% is the uncertainty. So these are the prior fluxes we have used. So this is the figure which gives that comparison of this measured CO2 and the model CO2. Model means we have multiplied with the transport component with prior flux, then add the background. So this is the model flow. So for the Tumba and Senegal, this is the picture we have got. So we can see that is even though the large scale variability, this model and measured is better over the Tumba region, but even though the discrepancy mainly over during the pre-monsoon season is the difference is large compared to the monsoon season. But for the Senegal, this differences are comparatively more, particularly during the year 2018. The region is the data gap we are showing for Senegal. The difference is more than some 50 some value for 40 ppm or something. That value we are omitted from the analysis. That is why there is some data gap. Here, Tumba instrument was not at the station at that time for these 2 months, during the 2018 to January, February. That is why the data gap over the Tumba. Mainly the Senegal, that observational model mismatch is more that we eliminated from the inversion. So with this thing, we have done the inversion, and that posterior flux after inversion is seasonal picture. We can see that this is the posterior flux for the winter, pre-monsoon, monsoon, and post-monsoon season. And this is the bottom panel shows the difference between the posterior and the prior flux. That is how much changes the inversion could bring. Showing this thing, but around the Senegal region, we are getting some lower value of this posterior flux, but over the Tumba region, the values are higher because of this two station. We cannot say that it is happening. Posterior flux is well represented, that we may not be aware of. We cannot strongly tell because it is accurate, but there are the inversion could bring that changes. That is what we are trying to convey here. And we also try to calculate the model concentration with the posterior flux. So the model concentration is that the green dots. You can see that there is during the most of the time the model and the prior and the model with the posterior are almost similar. We not distinguish, especially for this monsoon season, and there will not be little changes only. But winter time and pre-monsoon time, we can see some differences, and the difference is lesser over Senegal also. So we thought of what is the main reason, because there is a large difference between this observation and the model concentration of the Senegal. So from one opinion, we raised that maybe it is due to the prior flux. That yesterday it was also discussed that prior flux may not be correctly representing of that region. So what we are done is that we look at this biospheric flux, so that we we use that biospheric flux or this CASA model. So what then we thought of, why can't we use another model? So we tried to use that one model proposed by Mahadevan in 2018, that is BPRM, vegetation, photosynthesis and respiration model. So in this model, this biospheric model uses the meteorological data as well as the satellite data. So meteorological, from the satellite data, this is the schematic of the BPRM proposed by Mahadevan. This is Mahadevan ATR. You can see this different reference details are described in this paper. But it uses the satellite data for the enhanced vegetation index and land surface index, and then surface temperature and this radiations from this. We can use from this short-wave radiation from the meteorological reanalysis data. So then we can calculate the gross primary production and respirations in these equations. Then the net ecosystem NE can be calculated from the situation GPP and R. So this model VPRM we have implemented here, and we have done some simulations, for example, and we tried to compare with more observations and validating this thing with different biospheric model available. So I will show you on one figure of comparison between this VPRM and this CASA. for the year 2017 for 3 months. I can show that this is the first panel shows that VPR output from the June and August and October, and second is corresponding from the CASA. And you just see that the scale is that here it is -4 to 4, and here it is -1 to 1. So even though the patterns are matching, that there is a large quantity-wise, it is a large difference. It is almost 4 times higher than that. Is what yesterday I asked Dr. Sajeev also. Their model also is showing from the CASA. It is almost double their bias per flux. So in the this VPR, the features also more because it is high. Resolution is comparatively better compared to the CASA. We can do the distinguished features over the August months, but it is almost negative values over the entire Indian, the central India, but CASA giving the positive values over this region. And in the post monsoon also, it is that high value, positive values over this. That is what we are expected over this desert area or Rajasthan, but CASA may not be giving that much positive, almost zero values. So this, like other VPRM fluxes, maybe improve our inversion system if you use that. That is what we are trying to do with this next few months. We are trying to, we are running all these models, so we will, this takes a little bit of time to complete this work. So this work is going on. So in the case of the methane, what we have done is that methane we got another data from the Gadangi. So we use 3 stations for the methane inversions. So the fluxes that we are using, this is this transport sensitivity for this, the total transport sensitivity during the year 2017 and 18 for all the 3 stations. We compare that, this is the total transport sensitivity we are getting. This you can see that most of the influence is for the Peninsular India only. The transport, this station can mainly see the fluxes from the Peninsular India only. It's not from this. Cannot be represented from the, especially the more the flux region of the Indo-Gangetic plate. But sensitivity is more over the peninsular, concentrated mainly over the Peninsular India. So this is the prior fluxes we are using from the Andhra Pradesh, from the Edgar, and wetland emission from the Dada, and the emission from termites or emission from the CAMS. And the geological emission we have from the constant value from this paper we have used. So these are some of these, all these fluxes we use as a prior flux for CH4 or the region. So we computed, model the calculation with the prior flux and transport sensitivity. So this is the comparison between the observed concentration of methane or the 3 stations from Tumba, Gadangi, and Senagad. And the blue one is that model with the model. So now methane concentration is better in comparison with the CO2. That the model observation mismatch is lesser particularly over the station Tumba, and over the Gadangi there is some little bit mismatch for the model to the observation of the pre-monsoon season of the 2017. But overall, it is the model is representing the seasonal variability over the Gadangi. But Sinagad, here the model is concentration is higher than the observations, or particularly during the year 2017, almost all the year, but 2018 and all, it's almost a mixed value. But still, there are differences are more. If you look at the RMC here, RMC is the 36 ppb around for Tumba and 869 for this Gadangi, and 75 ppb for this over this Sinagad we are getting. So with this, what we have done is that we did a chi-square test and we have eliminated some data because if it is difference between the model and observation is more than 45 ppb, the chi-square values are very high. So we limited the values, observations where the model and observation is less than 45 ppb. So those values, observations only we are done for this inversion. So this is the posterior and prior flux of the posterior flux after the inversion, and this is the prior fluxes, and this is the difference between the posterior and prior fluxes. And but the differences we are getting is not that it's not very high values, but even though the water is on two order difference, but we get some patterns we are getting mainly over the regions near the Ganangi and Tumba, it is you can get prominent changes, but positive changes. But over the near region Senegal, we are getting the negative values because over the station Senegal, the observed values are lesser than the model values, so it will reduce that fluxes over this region nearby the Senegal observations. So in the case of seasonal changes, we look into seasonal changes. Posterior flux changes are more in the winter time and post-monsoon seasons. And the winter time, though we are getting changes in the southern peninsula region, but we are getting some little more changes over this eastern, southern, intermediate and eastern part of the Indian region, over the Bengal and Orissa region. And the post-monsoon season, the Senegal region and Tumba region, the fluxes are reduced from the prior fluxes. But over the eastern part of India and eastern region, the flux increased mainly because of the influence of the Ganangi stations. But the monsoon season, but the transport sensitivities, it is not much from the Indian region, but still we can see that some changes over this peninsula India, particularly over the Senegal, near the Senegal and General station, you can see some changes. Of course, for the post-monsoon season, we have got considerable changes over this near to station in Neral and Tumba, particularly the eastern coast of the Indian Peninsula. There are some observations, some changes that we could see. So if you compare with the modeled with the posterior concentration, the RMSE is reduced because with the prior it is 20 ppb was the RMSE, but the posterior it reduced to 14. Tumba region and Ganangi it is from 26 to it's reduced to 22, and for Senegal it is reduced from 22 to 18. So, but the corrections mainly, but some particularly the seasons, monsoon season, the corrections are very little because we have both that prior and posterior, the dots are overlapping. So that means there is not much corrections during the monsoon season. But pre-monsoon and winter season, post-monsoon and winter season, we could get some corrections. Almost or the three stations, so we could get the correction. This is the first time results we got from our inversion. So this is our kind of first time that inversion we are done with this Bayesian inversion over this region with our available ground-based systems observations. So maybe we will try to communicate. We prepared a manuscript and we will be trying to communicate with this results. So this is the summary of my talk. Eventually we did some optimization work for designing a network. So we are proposing a 17 stations using the transport Bayesian inversion and transport model simulations. And we try to do some inversions. So that is it is not a mature study. We are still going on only. So the results are not. You can authoritatively say it is a strength also. Maybe sometimes it may require some correction also. So thank you for your attention.
Thank you, Dr. CG. It was a really interesting and very informative talk. So we have some questions in the chat box. So yeah. So first question is from Vinu. He's asking, SNG during January, February and March, April, May suggests more sink. Why?
SNG means sink. Okay, posterior CO2 or methane?
Yeah, that Vinu.
CO2. That is because that modeled concentration is observation is lesser than the model. You can see this. This is why we are getting. So that part we need to work out why it is. After that there is a sudden jump in this. Your observation values are higher compared to what this because of this reduction in the concentration observation. That is why we are getting that fluxes reduced by all this region. So this we need to work out why it is happening. So we have to.
Yeah, and next I'm continuing questions with Minu, and then I'll go for other questions. So, what are the observational uncertainty used in case of SNG?
SNG we have used for CO2 we have used at 1 ppm, both observation and model. Maybe we have to increase that, I think. How much you expected this thing? Last measurements is less than 1 ppm or?
Yes.
But we need to work out because the uncertainty may not be. I don't know whether Shamil or Patra can be coming more. What is the uncertainty? Whether it is appropriate to use that 1 ppm for this data class measurements, or we need to add more uncertainty.
Yeah, generally for the surface site, how much uncertainty we use? Because for the satellite, I think we use 5 ppm or something like that, right? Everything.
No, I think this is difficult. From this plot, I would say that uncertainty should be more because there is a representation error and the measurement error. You have to put in the both errors in the inversion. And somehow this comparison does not look very good.
Yeah.
So I think 1 ppm looks to be too strong. So then if you see the next slide, you see that flux correction. Yeah, that is a very strong change in the local area. That looks too strong. So
we may be stressing more weightage observations. That means
yes, it's too much stressed, because then you see the synagogue is like becoming a blue dot, dark blue dot.
Yeah, correct, exactly.
So we do not have a dark blue dot because it's not so local. So if you increase the uncertainty from like maybe 3 or 5 ppm, then you will get bit smoother corrections. That is more realistic, I would say.
Yeah.
So you will not have the blue dot, but it will be a more homogeneous change over the area.
Yes.
That will be more realistic, I suppose. The range of 3 to 5 ppm somewhere, maybe 3 to 5.
Yeah. We'll try it because this is the first kind of our exercise.
No, it's very nice, very nice.
Okay, so we'll go next question. Okay, Harif is asking a related question: why model is not performing well at Srinagar?
Well, that is what we are expecting by this. Maybe one problem is its prior fluxes. That is what we are prior fluxes. Maybe sometimes underestimating, particularly the biospheric fluxes. That is why we try to provide better biospheric fluxes than at present CASA we have. But maybe VPRM with input maybe improve. That we have to look in that.
Yeah. Okay. So next question is Dr. Prabir. When you do these flux inversion for India, how are the fluxes outside the India boundary? We many time find flux dipoles with neighboring land and ocean regions. I think it is always better to show the whole region over which the inversion are performed.
Yeah. That is an interesting question. That is that fluxes, the contribution from the fluxes outside the Indian region mainly we attribute it to the background. From the background, we add this. The background actually we are computing the background from this. This is the sensitivity that transport that sensitivity terminates. It's well outside the Indian region. So where the transport matrices that particle terminates, from that points only we are calculating the background values. For the reanalysis more, the carbon tracker or the CAMS reanalysis, we have the mixing ratios and the contributions from the Indian region to this the terminating point, the fluxes from the fluxes. That also we are computing and adding to the background. So both from the outside fluxes and the terminating point mixing ratios are gone for the background. So in the total model fluxes, that point also we are taking here.
Yeah, but it will be very extremely difficult. Like for example, Bangladesh is in the middle, right? And you cannot escape Bangladesh optimizing Bangladesh fluxes.
Yeah.
Yeah.
It's impossible. Like the atmosphere is not discontinuous like this.
But at present we eliminated that.
No. I mean, so see, I mean, one thing I've seen also many others. Like, I mean, it's a general comment for everybody here. I mean, that I have seen many people just show the Indian landmass. I mean, we are. This is for science, right?
Yeah, correct.
So don't have to say that okay, this is a crossing to Pakistan boundary or Bangladesh boundary. This is science. So just be scientific. That for example, this long-lived species, there's so much boundary. Like there's no boundary at all. These ones. If you cut it like that, it is not. So even if you do the inversions and not optimize the fluxes in this outside the boundary, there will be problems. So be careful about that. I think you should show all the domain where you are optimizing the fluxes. Also, the ocean you cannot ignore because ocean has the fluxes also impact the land flux, or the land flux impact the ocean flux inversions.
Yeah.
So yes, be careful about this. I think we should not use political boundary anyway for these things. But it's not good habit, I think.
But one thing is that we found that because while doing the exercise in the case of methane, the contribution from the outside the Indian region is almost equal to the contribution from the inside region.
Yeah, it is even bigger for CO2. So this is the real problem with the regional inverse modeling. So if your boundary is like if your boundary is not well given, you have big difficulty in considering the fluxes and estimating the fluxes. So that's a known thing. But still, otherwise also you want to show a map which is more wider region, not by a very sharp boundary.
But we included that outside contribution to the background.
No, I mean, so the fluxes when you optimize the flux patterns.
Okay.
They had to be shown like for the optimization area, and the optimization cannot be done for like escaping Bangladesh here or Nepal there. You cannot because they are all contributing to the system for CO2 system.
Yeah, but somebody asked, what is the contribution from the Indian landmass?
No. So there, when you write the paper, you can give each country, no problem with that. Or you can decide not to give the country emissions for Bangladesh or Pakistan. That's fine. But those things when you make a number. But for the flux patterns, there is no number specific to any country, right? So you're not giving any country number. So I think you are safe perfectly for that. But when you give the number for the country, then you can give a number. Like you can write the number on the top of the map that India this much.
Okay.
Those are very useful. Obviously, people will ask for India. Obviously, you are an Indian scientist, so people will ask what is for India. But so those numbers you can always give. So this is the Indian value for this month or this area or this district. You can do all these things.
But you're telling that if you want to, then you put for example, for the old map, you put the flux and then do the inversion. That is what you meant?
Yes, we have to.
Yeah. I think your overall message, Pradita, is those fluxes which contribute to India, they should also be considered, right?
Like yes, because the Indian concentration, so you cannot escape the. I mean, and you cannot just invert this boundary of this mask. It is impossible.
Okay. What we are at present,
can I ask one question here, Yogesh? Can I ask?
Yes, we know.
This is rather our doubt, Prabir. This is our dilemma. See, these are 7-day back trajectory. Suppose those trajectory itself not covering immediate neighbors, how do we account them in our inversion?
What do you mean by they don't go beyond this? So any site.
For example, this map itself, you see that in the JJS, they don't go to our immediate neighbor like Bangladesh. So because that's a 7-day trajectory ends there. So how we account those flux areas in our inversion, because trajectory itself is not reaching out to them.
What do you mean? You look at this. Actually, they are going far beyond. Let's say Bangladesh may not be going to Bangladesh because you are not doing it. But see, this he's going to Pakistan. He's going to be in Indian Ocean. It's going to Bay of Bengal. It's going all over the place. It's going to Arabian countries.
So those all are accounted through the background. That's what we are trying to say.
No, you cannot do that, right? You have to optimize the fluxes of the whole region, wherever this in your box is. You cannot choose by country map.
Okay, then we average only for a particular area of interest. That is what you meant.
Yes, then you can always do your area of interest for the budget and the calculations, fluxes, and reporting to the country, reporting to the papers. Those are different issues.
Okay, thank you.
You have to take a whole square box.
Yeah.
Okay, so let's go next question. Next question is from Vinu. Do you have a seasonal cycle from VPRM over SNG?
Yeah, but this I didn't show this much. We have done some 2-3 years. Sorry. Yeah, this is mainly different by seasonal because it is a peak summer sometime or central India. So this is the monsoon time, monsoon and post monsoon. That is
Okay.
we have that all every week we have simulated for the years 2016 to 2020. So that analysis is going. So we have enough data at present, so we can do much better inversions during coming years.
Yeah. Now it's time to validate this with the observations.
Yeah, that also we're trying to validate.
Yeah, right.
Pramit has provided some data, so that also we're trying.
Yeah. So next question is from Harif. It is a very basic question. Should the network be planned on the basis of satellite coverage so as to reduce the retrieval uncertainties, which will be useful for spatial mapping of retrieved concentration?
It is not for satellite, it is mainly based on ground based because we use the surface fluxes and it's ground observations we plan. So it's basically it is the biaxial inversion and transformer sensitivities. So it is the network is mainly for the ground observations.
Yeah, Harif, I think if it's not clear, you can directly write to Dr. CG. Okay, so next question is from Smriti. She is asking, between VPRM and CASA GFED for the months of June and August, there is significant difference over Northeast region, while pretty much same pattern for October. Please comment if this some reason specific or some other issue. Some season specific.
Yeah, this is actually is a very good question. This is this northeastern part, the monsoon comes slightly earlier than compared to other parts. That is why in the VPRM, if you give the realistic data, the monsoon, once monsoon starts, vegetation starts growing, means that intake of so CO2 intake NE will be negative. That is what VPRM shows. But the CASA could not catch that thing. That is even August also it shows positive. That is one reason we believe that VPRM is better than CASA.
Yeah, right. Okay, so Smriti, I hope question is answered. So next question is from Mihir Prajapati. To minimize the limitations that IR sensors are facing in monsoon.
Yeah. So
any alternative for sensors?
That is the limitation of the IR sensor. It cannot penetrate the cloud. So monsoon season, the observations are limited. So maybe some other microwave or some other things. That CO2 cannot detect that. So we need to get some observations to make up, especially during the monsoon time. Satellite coverage is lesser.
Yeah, right. I think ground-based observation cannot replace satellites.
Yeah.
This Dr. Phillips he has told almost 20 years back. Yeah. Okay, so next question is from Chaitanya. He's asking, Gadanki and Thumba stations are lower altitude stations and is close proximity to paddy and other agriculture fields compared to Srinagar. Whether that has any local emission influence on methane fluxes, and the model was able to capture that, which may be one of the reasons for the higher mismatch with Srinagar. I'm not sure. He's writing.
Oh, this is an interesting question there, but I don't know why the Srinagar is differently behaving. Maybe one is that maybe sometimes it is altitude, high altitude stations, so maybe it cannot prior flux cannot be is not well for Srinagar. That maybe we have to tune for prior fluxes for representation Srinagar.
Thumba also is a light elevated side, right? No, or it's a plain.
Gadangi.
Gadinki, yeah.
Gadangi is almost plain, I think. It's surrounded by small hills, but it's nearby a lot of paddy. So plain lands are there.
300 meters above sea level, sir.
Okay, so it's not elevated. Okay. Okay, Chaitanya, I think your question is answered. So next question is from Dr. Mismatch. Mismatch varies considerably from site to site. Apart from modeling perspective, does the sampling, say frequency strategy, contribute to this aspect or no?
Oh, sampling on expertise you are like sampling experts. So I think site to site difference are like that is the one we are expecting, that is spatial heterogeneity in all of different sites having different local influence. For example,
Yeah.
what Chaitanya was telling that for methane, that Vinar and Garangi and Tumba, it's maybe there are some paddy fields or wetlands are there. But for Senegal, do not have that much influence on wetlands. So that flux representation is more. So spatial heterogeneity is there all over India.
Yeah, I think Shamil tried to write one question, but his writing has temporarily joined the chat. Shamil, if you are there, if you have any question, you can unmute and ask. Okay. So next question is from Pramit. In Northeast, we see significant rainfall during April, May due to the nor'westers and thunderstorms. This is unequally different from the rest of Peninsula. I think this is comment, not question. Okay. Yeah. So I think in the chat box, do we have just a second? Let me see if anything. No. I guess Vinu, just check. Many people trying to write in chat. It is writing no longer has access to the chat. So probably are they not able to write in the chat? So please check it.
No, actually that's a message when they are log in and log out.
Acha, okay.
Yeah, so that's
fine. Okay, I think this is these are the questions. We have discussion time is still 3 more minutes. If anyone has any question, just you can ask. Or then otherwise we'll close this lecture and then go for next talk.
Can I ask one question?
Yes.
So yeah, this is a nice plot. So I thought I used to ask one question on this plot. And so did you, because CASA used NDVI, which is like a, I think this is a normal CASA, right? And it is like a not the NDVI, I think is not updated with the recent data.
Yeah.
Because in CASA by Jim Anderson was published in 1997, so I think he did the work in 1995 or 3. I think, and you probably are using VPRM, MODIS, LAI, and FFR, and all the things.
Correct.
So maybe those kind of parameters are improved in the VPRM compared to this one. Is that?
Yeah. Maybe on the resolution also, it's CASA is 1 degree. The site is providing 1 degree only that it are taken, and it is up to modified up to 2016 only. 16 data only I am showing. After that, the carbon tracker is providing the CASA.
But carbon tracker is a kind of a very fake CASA. We are just doing a artificial 3 hourly fluxes. That is not to change the CASA fluxes, but just to introduce a 3 hourly diurnal cycle.
Correct.
So carbon tracker does not do anything to CASA. So the CASA still remains the original what you saw in the bottom row.
Okay.
That essentially remains the same. But then I am also curious what happens about the Rajasthan.
Yeah, Rajasthan, that is there.
Because there is almost no ecosystem, and you cannot have such a big respiration like a net emissions.
Yeah.
So there, because temperature, what happens is that net emissions. Okay.
So maybe you have to check the land classification. So if you mark it a desert, maybe not do this ecosystem so much, because that should be more like a neutral fluxes, not so big flux. But in June, it shows a huge amount of flux. It's like a normal soil, maybe. June particularly is very high, right?
June is it's because of the temperature.
You don't have a biomass there, right? It's just sand, not even soil.
Yeah.
But it includes that. Okay. Okay, correct. The Tar research
You can
also.
just take the land classification. That may help.
Yeah, we are trying to use that Bhuvan classification because at present we use that modest classification. Bhuvan classification we try to do this thing.
Yeah, you can introduce the extra layers on that. Yeah.
Yeah. However, CASA shows neutral almost.
Yeah, because that's a classification. Because nothing should happen there because it's a desert.
Yeah.
No soil, no plant.
Correct.
Correct.
Yeah. It should be there. Okay, I think let us thank Dr. CG Kumar for giving such a fantastic.
Thank you.
Yogesh, you are muted. Yogesh.
Yeah, sorry. So, okay, so thank you all, and thank you, Dr. CG. Okay, so we'll go to the next talk, and next talk is Dr. Vinu Valsala. He's well-known, and then since start you are listening, and then you are hearing from his side. But and then he is very well-known scientist in the field of carbon cycle in India as well as outside. So, but as his introduction as a customary, I will give a little bit brief introduction about him. So, Dr. Binu Balsala is BSc from University of Kerala in 1999 in physics, chemistry, and mathematics, and he did his MSc from Kochi University of Science and Technology in physical oceanography in 2002. And then in 2006, he did his PhD from Hokkaido University, Japan, in 2000, Oceanic and Atmospheric Sciences stream. So basically, he has many research interest area. For example, PCO2 biogeochemical modeling and data assimilation, planetary wave dynamics and associated particle tracer trajectory pathways. And his major contribution is basically OTTM, Ocean Tracer Transport Model, and Ocean General Circulation Models. And he has many awards and honors on his name. So, for example, in recently he got a Fellow of Young Indian National Young Academy of Sciences award in 16 and 20. And then in 2004 and 6, he was the Mitsubishi Yamamuro Memorial Scholarship, and then many other awards are there on his name. And he joined IITM as a in 2011 as a scientist D, and so currently he is continuing as a scientist F here. So I request Dr. Vinu just to give his lecture. Okay, yes, Vinu, we can see your slide. Hello, Vinu.
Yeah, I'm sorry, I got mute. Okay.
Yeah.
I hope you are seeing my slide. Yeah.
Yes.
Thank you, Yogesh, for the nice introduction. So today I'm going to talk about this estimations of the Indian terrestrial CO2 fluxes by inverse modeling. So this is a joint work by myself and Yogesh and our PhD student Shantanu Haldar. So most of the work I am going to show today here from his work only, from IITM Pune, and our strong collaborators are Siji and Nalini from SPL VSSE, and Shamil and Rajesh from Nice, Japan, and Prabir from Jamstech, Japan. So as we all know that since last 3 days, we were seeing this slide by various presenters that greenhouse gases are the fundamental factors for keeping the Earth's surface temperature warm on an average of 15 degrees centigrade. So there are two major long-lived greenhouse gases. They are carbon dioxide and methane. And if you look at the residence time of carbon dioxide is roughly 100 plus years, and its radiative forcing is approximately 2.16 watts per meter square, with a global warming potential if you gauge it as 1. Methane, however, have a short lifetime compared to carbon dioxide, with almost 1/4 or much less than global radiative forcing at the moment because of the lesser concentration, but 86 times global warming potential. So GHG is increased due to anthropogenic activities such as deforestation, fossil fuel, and cement production. And CO2 has been steadily increasing from 1960 to today by the direct observations in Mauna Loa. We all are familiar with this iconic map by many presenters, and today we have reached around 415 ppm. So now the recently IPCC AR6 assessed the change in effective radiative forcing from 1750 to 2019 contributed by various greenhouse gases such as carbon dioxide that stands the highest, and then just immediately next to that methane, nitrous oxide, and other halogens are lined up with some cooling effect introduced by the aerosols. So now, what are the various methods and challenges involved in the global carbon budget estimates? That's what the major focus of my talk. So we've been familiar with the bottom-up methods. But what is bottom-up method? For example, it is a process-based modeling and inventory-based modeling and bookkeeping-based modeling, etc. will give you some kind of estimate how much is CO2 is exchanged or methane is exchanged between the surface of the Earth and to the atmosphere. But however, there are challenges. What are the challenges involved is there are incomplete processes, that because we don't know many of those processes yet in models, such as forest regrowth and degradation, wood harvesting, etc. It's very difficult to keep a track on. And inaccurate bookkeeping most of the time induce a large uncertainty in the such estimates, and management practices also, for example. Now, poor knowledge about the inventories adds a lot, especially talking about the Indian inventories. We are still struggling with large uncertainty existing in the inventories of the various greenhouse gases. Now, the second methodology is the top-down methods, which is more scientific in the sense that the inverse estimations of the fluxes. By combining the atmospheric CO2 measurements and models, we kind of come up with an estimate how much can be the approximate emission scenario for a particular greenhouse gas. So, however, that also has challenges. One is the limitations in the prior data sets are not well derived. For example, we've been listening to the talk by other speakers saying that prior data sets has large error perhaps in Indian region. That can be one reason why Senegal data cannot be modeled well. Okay, and then intermodal differences, that is another thing, and the transport model errors. So transport model itself has errors in various of its transport mechanism like mixing, convection, representation, etc. Then the uncertainty in the interhemispheric CO2 transports in models also had some challenges, and model resolution issues. So all these add to the top-down methodology to the challenges too. So, and the third point is the sparse observation. So we know that although we have a large number of data points by satellite, but the retrieval uncertainty in the satellite is much larger than the ground-based stations. But if you look at the ground-based stations, you see there are sparse coverage. There's no dense network of stations to constrain any model. So that is adding another challenges to this estimate of the greenhouse gas budgets. Therefore, we need a more focus on refining the global carbon budget estimate. That is one thing, and global and regional efforts in improving the observation and understanding the processes are also become essential. Now, here comes the part of the inverse modeling. So there are many students are also here. So I will give you some background about or some fundamental about how the inverse model works. So inverse modeling, what we are trying to do here is we try to minimize the cost function. Say cost function is the total error present in the flux and the concentration. Say, for example, represented by this particular equation. And this has various terms. The x represents the posterior fluxes, and the x naught represents the prior fluxes, and z is the observation of a particular greenhouse gas under consideration. And b and r are the prior variance covariance matrices for the flux as well as for the observations, and H is the transport model or the transport response function to the given implied fluxes. So this is the schematic representing the Earth surface and various emission and absorption scenario and the various observation and transport. So we have emissions by the fossil fuel and fire and ecosystem exchange of greenhouse gases, and we have oceanic exchange, and atmospheric transport brings this concentration well mixed throughout the globe, and that we can measure by using either surface-based stations located on the ground or by using satellite. So we have, if you know the information about the transport as well as if you know the direct observation of the concentration, then you can inversely estimate what is the exchange of these greenhouse gases between the Earth's surface and the atmosphere. So that is the basic idea of the inversion. So now the right panel shows that this is how we do global inversion in a transcom manner. That means we divide the globe into a coarse resolution homogeneous regions, and we do try to optimize the fluxes coming from this each region according to the transport and the observation by minimizing this cost function which is shown here. So this is the basic idea of the inverse modeling based on the transcom principle. So this is a Bayesian in statistics we use here. Now, how this methodology works, the methodology inverse modeling and Bayesian inversion. So what happens is that if you have a model domain, assume this is your three-dimensional model domain, and you divide the global surfaces to various well-defined regions, say region 1, 2, 3, 4, 5, 6. 6 regions are shown in this cartoon. And what you do here is that first you need to generate, so your purpose is you have this cost function. The Bayesian statistics say this cost function, this error is minimum if you optimize the fluxes in this manner, that your prior fluxes added with certain correction term. So this correction term is what we are looking at. So what are the components of this correction term? There is a posterior uncertainty or posterior variance covariance matrix you get by results of this combining the transport and observation, as well as this is the mismatch between the observation and the model. So as long as this mismatch is non-zero, there is a potential that you can correct your implied prior fluxes. So here, what are the elements you require? You require basically H. H is nothing but the model transport vectors to the observation location. So how do we calculate that? Suppose if you have this well-defined region and you force the model with some implied fluxes from this region and allow the atmospheric transport to take it over the entire globe, then you make the measurement at the station location. What is the response at those stations in terms of concentration by this implied fluxes? So that will become your element of H. Then you can arrange this element of H, the H matrix in this particular region. That means from the region 1, what are the sensitivities captured as the station number? These are the station number T1, T2, T3, T4. They are the station number. So they will calculate the response of the H with in these station numbers as generated due to the implied flux in the region 1. So you will get those response numbers here. And then for the then you do with the region 2, you repeat the same experiment and calculate the the response arrived from region 2 to those station location. Then you put it in the next column. So like that, you construct the H matrix. So this is a model response matrix, you can say, with respect to a given implied fluxes. So once you have the H matrix, the rest of the thing what you need is the variance covariance matrix. For example, you have R, the model observational variance covariance matrix. It represents how the observational errors are accounted in the system. So there are two types of error: only representativity error, or the model error, as well as the observation error. And then you need a flux error. So flux will have some uncertainty. So that will compose your matrices R and B. And then if you have all these terms, then what you next need is the mismatch. Your your station observation, which is Z, and Hx naught. Hx naught is nothing but the model concentration. Z is the observation. So if you have this mismatch and all the rest of the metrics, you can calculate the posterior flux or the correction term, which you can add it to the posterior prior fluxes. Then you will get the total posterior fluxes. And an additional terms comes here is that the posterior uncertainty, which is encapsulated in this particular matrix, which can tell you how much the prior uncertainty has been changed or reduced by optimizing using the observed concentration of Z. That is the system says. Now this is quite direct because you can measure the model concentration at the station location quite directly. But if you have a satellite data, which is not a single point concentration, a column concentration. So you have to average the model concentration by giving appropriate weighting function for representing the satellite model XCO2 data. So that also you can convert using this equation, which is taken from Basu and Patra 2021. So now this is how the basic inversion methodology works. So your basic task is to generate this the response, the H matrix, as well as the variance covariance matrix and the data minus model misfit. So this is quite similar to any assimilation system. What you're trying to do is you're finding certain correction terms. Okay, so in the Bayesian inversion, we do with coarse resolution regional matrices and try to invert and find the correction. So this is the basics of the inverse modeling. So the literature on various Asian carbon budgets are written here. So the transform inversion started perhaps in 2004, published in Gurney's paper, saying the Boreal Asia. So these regions are characterized with a certain homogeneity in the fluxes. So here let us focus on the Asian region. So Boreal Asia is a sink of minus 0.36 as per Gurney, and tropical Asia was a source of this much, and the temperate Asia is representing somewhere around this this East Indian and Indonesian continent. Temperate Asia is a sink of minus 0.41. And the Swathi et al. Did perhaps the first inversion done from the Indian Institute is perhaps Swathi et al. Updated this minus 1.5 petagram sink of temperate Asia. And then South Asia. If you come to South Asia, the various budget estimates are by Patra et al. 11 and 13 are various numbers they have come up with. So as the methodology advances, more and more data come up, then more and more updated estimates of the South Asia has come by various paper by Jiang et al., Sarvarich et al., Thompson et al., etc. So later by GOSAT group that found that using the satellite data, the percentage uncertainty reduction over the South Asia can be up to 25% by Takagi et al. And Makhdousov has updated to 25 to 27%, and Saiki further updated this number as to 27 to 30% if you have more satellite data in the inversion. Now, let us take a journey of inverse modeling in IITM. So this is how we have progressed in last 10 years. So there are two different channels is shown here. So first in IITM, what happened, we started the observations of carbon dioxide and methane from Sinagat somewhere around 2009. The station got established. Then by 2015, we have done a lot of experiments on comparison of observed concentration and forward model concentration taken from TM3, for example. And Devi, who was the part of this workshop, has published his thesis based on this data collected and comparison of that data with various forward models. Then what happened is that at the same time in the SPL that CG was presenting in the last, they also started envisaging the idea of GHG modeling somewhere around 2014-15 time. And we had some communication between them. Then it got progressed further, and their focus is basically towards the Lagrangian modeling of the regional CO2 enhancement. That's what they were interested in their approach, and that has evolved for another 2 years. Then what happened at IITM is that then we started initial discussions on inversion establishing in IITM itself. So that was also a time when we started the GHG workshop. That's our first workshop where we have given some taken some hands-on training also from Prabir and all to do how to do the basic inversion in an in-house setup. So that we got established in 2017, and by 2018 we had but to do inverse modeling you need access to a transport model. So that's the basic requirement. So we got some access to the niche transport model. So Shamil has provided us the code, and that has been ported to IITM by around 2017-18 time. So at the same time, then SPL was thinking about doing some kind of OSSE of optimal network station design. So they started discussing about that and producing dividing the entire India into well-defined boxes and doing back trajectory and see how the sensitivity, the output footprints evolves, etc. Then we come up with the idea that we jointly learn how to do this optimal network design using incremental optimization, which CG presented recently. So this input was very important for us to grow in our inversion also. So and then we further taken this niche transport model and the transcom inversion. By 2019 we have set up the niche TM and validation of all the model basic validations all completed, and we established the inversion system also in 2019. And at the same time SPL was progressing towards Bayesian inversion or use and OSSE. So they have also completed a work of OSSE using Bayesian inversion. So the SPL channel is basically about the basically by the flux path modeling. So they use the Lagrangian trajectories as their inversion setup, but we use a Eulerian trajectory. That means we have a Eulerian model which is niche TM, and we went ahead with the more global inversion using the transcom protocol. Then as of today, this is the achievement in this both the teams, for example. So we have a complete working setup of transcom inverse modeling, whether it is cyclostationary or time dependent inversion is established by 2021 here, and a couple of papers got published, and Shantanu was working to make this possible in last 3-4 years in IITM. And in SPL also they also come up with regional inversions of carbon dioxide and methane. We just listened to CG. They also have some regional estimates of Indian CO2 fluxes and methane using the trajectory model. So this is the total journey of inverse modeling in IITM and SPL, and for which this greenhouse gas workshop one was very useful. So we were telling that in the earlier also, it was very instrumental and very timely this happened. So we all could learn and grow in this particular aspect. Otherwise it was quite unknown to many of the Indian groups. Now coming to the niche transport model. So it is National Institute of Environmental Studies transport model by Makshistov et al. In 2008. It's a global offline atmospheric tracer transport model, and this is what we got and we established at the IITM, and it is run with JRA 25 JCDAS meteorology, and it has a 3-hourly varying PBL heights taken from ECMWF, and its resolution is 2.5 into 2.5 and 17 vertical sigma level. So this is the basic structure of the model, and this snapshot shows the atmospheric CO2 concentration simulated by this model on the surface level. So now, to validate the model, what we have done, we have taken the CASA fluxes from the Indian biosphere, and this is an ecosystem exchange by the Indian biosphere as per the CASA data. So CASA, basically carbon tracker data, we have taken here, and you can see the seasonality of sink, especially in August, September, October. You have a sink, and then you have some source condition in May, June, July condition, and then you have a uncertainty, or also plotted here as 3-hour uncertainty, and then this is the annual mean fossil fuel flux, again taken from carbon tracker over India for the validation of NISTM. So this is the annual mean fossil fuel fluxes we adopted. Then we run the model in forward, and then we try to learn how to run the forward model at IITM and how to validate it. So this is the validation plots for various locations, say monolova. So CT means control monolova, and GOSAT monolova, and monolova observation. So we have compared 3 data sets in this particular time series. You can see that the model NISTM successfully capture all the seasonality and the trend and very nicely in monolova station. And then we compare to Seychelles. Seychelles is a southern part of the India, and it's on the oceanic station. And Seychelles, why we particularly show here, because its seasonal cycle is much different from monolova, and it has much shorter seasonal cycle and much difficult variabilities within the season, and that is also captured very nicely by NISTM. So the control simulation, which is shown as the green line, you can see that has nicely capturing the observed values of the seasonal cycle. So it's a very encouraging that this transport model is doing a very good job for our inversion purposes. Then we compare with Cape Rama. Here comes the challenge. Cape Rama has no data in between, and Cape Rama is good in the early December and then the late monsoon season. But during the dry season, Cape Rama also had a observation shows large values as compared to model. So model has the difficulty capturing it. So it is not just the problem of the model. Perhaps the fluxes may not be representing well for the Cape Rama also. Now, if you come to Sinagat, the comparison is even worse, because Sinagat also had large amplitude in the dry season, which model cannot represent at all. So we were discussing this extensively in the last 3 days, why Sinagat cannot model well. So various recommendation came, flux may be inaccurate. We are working on that, and transport model maybe may not be able to represent the terrain and topography. That may be one reason, or some of the outlier maybe we need to filter out from Sinagat. That is another discussion we are also doing. So this is the various comparison of observed data, comparison between NIST transport model and the observation. So these are the key points written here. I am not reading because most of them I already discussed. Now what we have done is we have done a typical experiments, because in the earlier talk, CG has shown that what are the optimum locations to start a ground-based observation from India, so that it can capture the maximum footprint of India. That is what in Nalini's paper discussed. But we asked the question the other way around. What are the observational data we can get from the globe or in and around India, so that even some of the footprint of India is available in that observation? So this is a complementary question to what Siji has asked in the earlier case. So what we have done is we used this NISTM model to simulate the response functions or the atmospheric background mixing concentrations of the CO2 generated due to Indian fluxes. Say what we did is we bettered the model with the Indian biospheric fluxes and run the model in several ensemble cases, and we assembled them and seasonalized them and represent that this is the discernible atmospheric concentration dissolved in the background, which is contributed by the Indian footprint or Indian emission or Indian NE map. So that is what shown in this map. So what is shown here is that within this cone of influence during December, January, February, about 0.1 or 0.2, 0.3 ppm of concentration of enhancement is embedded in the background due to the emissions or the fluxes from the India. during DJF, and this is during MAM, and this is during JJA. So JJA, you have a biospheric respiration exceeds, and then you have a larger positive concentration, you can see, and due to the monsoonal winds and meteorology, the shape get changes, and this is at the surface enhancement. Okay, and this is for the September, October, November, and this is due to the biospheric plus. So same can be calculated for the fossil fuel also, because we have a forward model. We can do various combination of simulations. So the scientific understanding from this experiment is that what all are the region, whether a ground-based station or a satellites can look for to get some information, at least from the fluxes originated from India or fluxes related to the Indian concentration. So that's what we try to identify from this in this work. So what we found is that here the enhancement means at any given space and time, the discernible concentration of atmospheric CO2 from a global background that is generated by the Indian fluxes. So this information is important because any observation, say satellite, if you look at ground-based station, resolving it gives a value addition in the Indian flux scenario, because it represents the true Indian footprint information. So yeah, we can check the same thing for in the upper atmosphere, say 850 hectopascal and 500 hectopascal. As you go up in the atmosphere, the area influence goes even larger and larger, because it's in the upper atmosphere. It's well mixed in that case. So we have found this area of influence. Then what we have done is we calculated the column average of Indian enhancement for each season, and we make an envelope of 0.2 ppm and 0.5 ppm. Okay, then we counted the number of satellite XCO2 available from either GOSAT or OCO2 representing this enhancement. So if we count the number of satellite observations per day in each season from GOSAT satellite, GOSAT covers this footprint basically in DJF quite well, and in MAM also reasonably well. But if you look at JJA, when we have extreme cloud condition, the GOSAT satellite seldom seeing any footprint from India, and this actually tells the community we need more ground-based station to cover our JJA season. But if you look at the OCO2 satellite, they have better coverage, especially in DJF, it is covering the Indian footprint better, and MAM also. But in JJS, it has more coverage as compared to GOSAT. So GOSAT, so the OCO2 coverage during the monsoon season is better compared to the GOSAT. So this information is useful because this is the pixel actually going to give some constraining of Indian terrestrial fluxes in any satellite inversion using the Eulerian method. So that's what we did this experiment. The same, then what we did is we used the methodology of Park et al. To calculate how much of this Indian footprint enhancement is actually captured by the already existing satellite data. So we could calculate it around 0.1, 0.2 ppm is captured. Actually 0.2, 0.3 ppm, etc. is captured by already the existing satellites is capturing that many enhancement, which is consistent with what model predicted enhancement. So satellite is capturing that. So satellite data is useful, but we need a better coverage. For example, the GOSAT does not give such coverage in the June, July, August which representing the Indian footprint. So we have verified this with the Park et al. Method and the Hakkarainen et al. Method. And in the both method say that the existing satellite do capture definitely the Indian enhancement over and in and around the Indian region, and the cone of influence we could exactly pinpoint because we have a modeling capability. Then we have done the same for the OCO2 also. OCO2 capture better enhancement up to 0.3, 0.4 ppm enhancement due to the Indian fluxes for any given seasonal scenario. So that was also an encouraging point that OCO2 that may constrain the Indian fluxes better. Yesterday, Saji Philip also saying the constraining offered by the OCO2 data over the Indian flux seasonal cycle. So this is a published work in Shantanu's PhD in Haldar et al. In 2021 JGR. Then we went ahead. We have done several inversion experiments. We have done a suite of inversion experiment. What we have done, we taken the surface stations from the global view. We had a 82 surface station on global view data set, and we add Sinagat, and we add Scaprama, and we subtracted Sinagat, we subtracted Caprama. We do a lot of combination. We added satellite pixels for as XCO2, and we subtracted satellite pixels. So all these combinations of observations we utilized for the inversion using NISTM. So, and we found out what are the various utilities of the Indian station in constraining the Indian region as well as the neighboring region, if at all the data is of a very good quality. That we should not forget. Quality is also a matter in this inversion. So many inversions are done. I'm not showing the result of all, very key few results only we are showing. So our inversion setup, we did two type of inversion. One is the regular Transcom 22 region inversion, so which has the temperate Eurasia, which encapsulate Indian continent mass. So which is basically a combination of a larger Eurasian mass and Indian mass together is called a temperate Eurasia, Eurasian temperate. Then Indian tropical is the oceanic region, and tropical Asia is the Southeast Asian region is called the tropical Asia. So we have done the inversion. So we have the prior fluxes are shown in the thick black line, and the various posterior fluxes for the annual cycle are shown in the other colored lines. Then we have shown here whether what happens if we added the Synagogue, if we subtract the Synagogue in the inversion, how much the flux condition changes. The results we got is that Synagogue data suggest an overall source of temperate Eurasia. Temperate Eurasia is a very big region, not very far from India, and it's a very large region. So constraining such a large region from one station in India may be not very valuable. So, but still we did this exercise because to know for gaining some understanding. So we found that Synagogue data suggest an overall source of temperate Eurasian terrestrial fluxes at a magnitude of 0.1 petagram carbon per year, as opposed to minus 0.23 sink when none of the Indian stations are considered. But this can be quite challenging to constrain because Indian station is also not well sufficient for constraining such a large region. And tropical Indian Ocean and tropical Asian inversions results are shown here. And the right panel shows the uncertainty reduction achievable for the temperate Eurasia if we use a station from India or if you don't use a station from India, etc. is shown in the right panel. So these are the key numbers we got starting with prior and then posterior for the GV cases, and with no CRI, no SNG, and with no CRI and SNG, how much is the fluxes, etc. is summarized in the table. So in adding Synagogue data and CRI data to the inversion make the region more towards a source. This is exactly where we're discussing, because during the dry season, these stations capturing larger, perhaps local CO2 influences. Then what we have done is we have subdivided the Transcom region into another 8 more regions. So we divided the in and around Indian region, cut into more high resolution. So we separated India from temperate Eurasia. That is number one. Then we separated the North Indian Ocean into Bay of Bengal and Arabian Sea, and the South Indian Ocean into tropical 2 region and southern 2 region. So total 8 regions we subdivided this so that our metric size increases, not tremendously, still it is a coarse resolution. So our intention is to see how as an Indian landmass alone can be better constrained by data either from station based or from satellite. That's our intention. So this is our well-defined region. So we got new regions called MTE. That means the modified temperate Eurasia, and India, and Arabian Sea, Bay of Bengal, tropical Asia, Western Indian Ocean, Eastern Indian Ocean, North Indian Ocean temperate, South Indian Ocean temperate. So we have subdivided it and calculated the prior and posterior fluxes shown in this map. So if you see that the modified temperate Eurasia does not have any change whether you cut India or not. Okay, there is no difference because the region is so big. But if you come to India, so this is a central plot. So this is an inversion. So prior says there is a mild annual sink by India, but it is enhanced by the inversion, considering the data from India, either Caprama or Synagogue or a combination of Caprama and Synagogue. That is why the seasonal amplitude of Indian terrestrial fluxes increased by doing inversion with a more fine resolution Transcom region. That means if you separate India more fine from the rest, and we can see more influence of the Indian station. And if the right panel shows the uncertainty reduction. So you can see that the uncertainty reduction in the summer monsoon season by Synagogue and Caprama is very little for Indian region. That is obvious because during summer monsoon, the Synagogue and Caprama capture the oceanic signal. So at the same time, ocean gets more uncertainty reduction by these two data. So there is a benefit if you separate the region in the Transcom with the ocean versus land and land versus larger land, then you get better benefits. And so the value addition of Indian station, for example, Synagogue is clearer when we separate India from rest of the temperate Eurasia, and a maximum UR achievable by Synagogue is 30% during the January to March, as well as from October, November, December, because that's the time this footprint capture the Indian landmass. The rest of the time it's capturing the oceanic signal. So that is very obvious. Now the right panel bottom shows the the model assimilated concentration. That means after inverting the fluxes, the prior fluxes, you get the posterior. Using the posterior, you can again run the forward model. Then again you can compare your Synagot modeled data as well as the observation data. So we can see in the dry season, April, May, June, the model is not get assimilated at all well. And that is all because the observation is too far away from the model simulation that cannot be captured well. The model uncertainty has taken care not to stress the model more towards the observation in that season. But if you look at the October, November, December, the assimilation captured the signal reasonably well. So that means if the data has high quality, there is a good promise that we can utilized Indian station data to optimize the Indian terrestrial fluxes better. Now you may be seeing more dots shown within the Indian region in this map. So those dots represent the proposed station by Nalini. Previous Saji has given the presentation. So if those data we utilize, what is the benefit we can achieve? We have to check that also. They already calculated the benefit of Nalini station in the total uncertainty reduction for Indian fluxes, but that is not complete enough, because that data can also constrain in and around India also. Not only India, it can constrain the neighboring region also. So that is the purpose. We also checked the utility of those new 17 stations to constrain the neighboring region of the India in the global inversion framework. So I'm going to come to that result in a while. So before that, this is our interannual terrestrial biospheric CO2 fluxes from the time-dependent inversion. So we thanks Prabir so much for guiding us through how to get the TDA inversion correct in the transcom using our NISTM model. So we have achieved it. So this is from 2009 to 2016 we have inverted. So this here we use the CAMS prior fluxes. CAMS is the combination of various intercomparison priors they have produced. So we have used that, and CAMS also produce a posterior, and prior and CAMS posterior is shown within it. And we have also shown this the 73 plus GB plus satellite inversion and 72 GB plus satellite inversion. That means including Synagot and not including Synagot. We have done various inversions. So you can see the seasonal cycle with the maximum dry season emission and the monsoon season, post-monsoon season sink and etc. The seasonal cycle is nicely reproduced in the TDI. And now if you take the difference in the TDI inversion with and without Synagot, we can see that the inclusion of the Synagot implementing certain mismatches in the seasonal cycle. Whether it may be true also, because yesterday also we have seen the satellite inversion does not capture the Indian seasonality well. So the Synagot, but if you include the Synagot, it is changing the seasonality a little bit. That is one point we need to note. And also it imprints some changes in the interannual cycles, because it imprints some changes in the seasonality. So the right panel shows actually here before inverting, we have corrected the Synagot data. So how we corrected is that we have taken the trend from Mauna Loa and we adapted it for Synagot, because they are kind of belonging to the same latitudinal circle, but there may be some uncertainty in doing so. So that the corrected Synagot data is shown in the red dots here, and the inverted Synagot data is shown in the blue short line here. So the difference is something around the residual is less than minus plus or minus 10 ppm. So using this Synagot data, we are able to invert the and also the satellite data. Here also we include the XCO2 data from GOSAT in this inversion. So the bottom line is this is the first study which inverted the biospheric fluxes of India using Indian observation of atmospheric CO2. So we say it because Synagot is attempted here. That's what we are saying it. And the TDA inverted Indian biospheric fluxes from 2009 to 16 indicate no apparent trends. There is no such trend in the NEE flux, which is also consistent with the South Asian regional results of Thompson et al. 2016. So this is also a product we have come up with our in-house inversion. Now this shows the seasonal cycle mean uncertainty reduction contributed by the Indian station and satellite. So what we could do, so the ground-based station gives a larger uncertainty reduction, especially here the ground-based station we check this Synagot only. So therefore in June, July you don't get any uncertainty reduction because they are coastal station. The air mass coming from the oceanic region. So apart from that, whatever improvement we getting is from the station data, not the satellite data. The satellite data enhancement or the uncertainty reduction benefit is very feeble, and that may be because the satellite data in earlier slides I have shown, the real enhancement captured in the satellite XCO2 representing the Indian footprint also is limited regionally and temporally. So that limitation kind of adds to the inversion. So satellite may not give us such a large benefit only for the Indian terrestrial construction of the, constraining these fluxes. Okay, so that is the point we want to tell. But the station data has large value addition. So come up with good ground-based station data. We will benefit a large in the Indian greenhouse gas budget estimate. So this is the message. Now going further, this is another plot showing the interannual anomalies of the time-dependent inversion CO2 fluxes. We have seen that it's a bit complicated to explain because this is only for Indian region. Okay, so we separated India from rest of the Eurasia and etc. So it has a much more chaotic signature, and there is no clear association with the El Nino or IOD. But some interesting point is that Indian basphoric fluxes correlates with the ENSO appears significant, but it appears significant, not very much. Maybe the limited duration of the time is also one reason. However, the inversion of Sinagat data suggests the ENSO NE correlation is negative. So that means Sinagat is kind of trying to reverse the relation. A point it needs further investigation, whether the Sinagat data quality is the reason or is it a true thing that we need to further investigate. Maybe in future some more stations come up, we can cross-examine the ENSO NE relation in India with more data inversion from Indian data, more inversion experiment with the Indian data. Now Indian NE correlating with the IOD. IOD is another climate mode near the in the Indian tropical ocean, appears significant, however turns to be insignificant while including Sinagat data. Basically Sinagat data messing up this relation, either it's changing the phase or change and making the relation weaker. So we kept this thing for a future research. Perhaps we need more fine tuning of Sinagat data with removal of some background etc, and then try to see how this relation get evolved. Okay, so it could be related to the seasonal differences induced by the Sinagat in the inversion, and this is a typical seasonal cycle in by inverting using Sinagat and without Sinagat. I think most of it I have discussed already, so I am skipping this slide. Now this is the climatological seasonal mean posterior regional fluxes by inversion using our in the transcom inversion by keeping India as a separate from the rest of the global regions. So this is the integral of this already we have discussed in the line plot. So I am just going ahead. Then the last thing I want to highlight in today's talk is that as Siji just now presented, they come up with 17 new stations to start in India, which can represent the Indian footprint in a regional inversion perspective. So what we have taken up this station and put it in the global inversion and see, in addition to India, what are other regions can get benefit from this station, and we can rank them. Okay, so what are those stations among those Nalini station recommendation? What are those stations which can not only benefit India but the neighboring region also in the global inversion? When we do so in the Transcom 22 region, the Eurasian temperate Eurasia, which is a very large region, has some benefit. If you use the 17 new stations from Nalini, we rank again one by one those stations and we shaded from purple color to the green color or the red color. We can see the maximum uncertainty reduction achievable is around 40% only, which is true for even Indian region as per the Nalini's paper. But tropical Indian Ocean does not get any additional benefit by adding Nalini's 2 station, because maybe some stations will get some benefit, but not some areas will get benefit, but not much, especially the entire Indian Ocean. This Indian tropical means entire Indian Ocean as a region, it will not get benefit. Now tropical Asia, however, gets some benefits because some of the stations representing the northeast, and that may kind of capture the footprint of the eastern Asian region. So tropical Asia gets some benefit. So these are the conclusions. The uncertainty reduction for temperate Eurasia can be achieved by 24, 36, 55, etc. Using various combination of satellite and 17 new stations, etc. But it appears that the 80 GV plus satellite performs better than this news tropical for the Indian Ocean. So Indian Ocean is not benefited much because the Indian Ocean here is a big region as that original Transcom region. But if you divide this region in the India as well as tropical Asia, so we see that if you cut the India from rest of the world, this Nalini station can really bring a lot of benefit in constraining the Indian fluxes. So that is the additional benefit we brought here. that this 80 GB plus 70 new configuration can reduce the uncertainty of Indian fluxes by 70% in all season. This is much larger than the number they themselves reported. That may be due to the coarse resolution inversion nature of our system. There is they have a fine resolution inversion because of the particle trajectory. So that difference may be bringing some overestimation of uncertainty reduction in our experiment. So that is one thing. So the bottom line is that these new stations proposed has a larger value addition, especially in the oceanic region. If you look at the Arabian Sea, the new stations will add larger uncertainty reduction up to about 20% during kind of most part of the season. In the Arabian Sea, get a larger benefit from these new stations, and Bay of Bengal to get some benefit during the let's say February, March, but not much in the other. But Western Indian Ocean, and which is further south away from India, will not get much benefit. So these stations are good not only for Indian flux constraining, but also for the outside in neighboring region plus constraining is these stations are useful. So here I summarize my talk saying that with the help of NISTM, and we were able to find out the atmospheric enhancement in CO2 contributed by the Indian flux for each season. And the surface level CO2 enhancement due to biospheric flux is as large as 1.4 to minus 2.6 ppm. During June, July, August, and SON respectively. And the model results give a guidance to extract similar enhancement captured in XCO2, because we need a model guidance where to look in the satellite XCO2 to find out the Indian enhancement. So the results show that the average enhancement of plus or minus 2 ppm can be captured in satellite XCO2. It's a vital information for the inverse modeling. And the value addition of the Indian station, some example Srinagar, is clearer when we separate India from rest of the temperature Asia in the transform inversion. So this we need to do because we can constrain the local region better if you cut the region. And Srinagar data suggests an overall source of temperature Asian terrestrial fluxes at a magnitude of 0.19 petagram carbon, which is not a good thing because it is temperature Asia is a larger region to constrain by one Srinagar data. Now continuing, the interannual inverted Indian biospheric fluxes from 2009 to 16 indicate no apparent trends, which is consistent with the paper of Thompson et al. Then Srinagar suggests a more CO2 source in dry season and more CO2 sink in the growing season over India. So this is again CG's results also showing the same, more sink in the growing season. Or in the early January, February, they have more sink. Now, seasonal amplitude of biospheric fluxes over India enhanced during El Nino compared to La Nina, which is another consistent result what noted in the North America by Crowell et al. Also. Now, we have also checked the Nalini's new stations, and we found out that 70% benefit can obtain, but this may be some exaggerated because our system may be an overdetermined problem in that case, because so much data for within India, which may be an overdetermined problem in the Eilurian inversion. Now, this 17 new station, however, add a very small constraint reducing the tropical Asian fluxes. And so the major effect of 70 stations can be noticed for Arabian Sea with some benefit of 25% uncertainty reduction. So these are our major results. So this was all possible that we had a handy atmospheric transport model with us, and we also got the education of inversion using during these greenhouse gas workshops in first and second, etc., which were helping us to do, and also the interinstitutional collaboration. For example, we all learned together with the SPL, CG's group, and our group. So that is one important. We need to communicate and try to learn, maybe conduct more meeting and workshops to learn and interchange our technology and knowledge. So with this, I conclude my presentation, and I thank the organizers for giving me this chance to present in this workshop. Thank you.
Thank you, Venu. It is really a very interesting overview of inverse modeling, which is developed at the IITM. There are questions in the chat box. Harif is asking, can ERA 5 meteorological data 0.25 degree resolution can be used in NISTM instead of JRA data? Is there any analysis or merits or demerits?
Well, first of all, we are not equipped with transferring the meteorology data suitable for NISTM. Actually, that software is with Shamil's group. We do not have that software, but we can basically have it. We can take a different meteorology and utilize for the transport modeling. And the benefit or demerit, we have to look at the result, whether that will capture the seasonality better. But so far, the JCDAS data are doing a very good job in in pristine environmental stations. That's what I was trying to show here. So this clearly tells that this JCDAS data are doing a very good job, especially capturing seashells is pretty amazing. The seasonal amplitude and small changes within the seasonality, etc., are able to capture. That means it's the quality of the transport, which comes from the meteorology, which comes from JCDAS. So I think it is okay. But one can replace. If you have such software to convert the data, we can replace it also.
Yeah. Okay. Thank you. So Imran is asking, I did not understand why you correct SNG data, which is in situ observation.
The correction is that, see, this is the problem. According to the local emission scenario, the data may be of a little bit of representing not a large footprint, but with more influence from the local footprint. So what modelers can do, this is a practice in Transcom in protocol also. They try to imitate the trends from Mauna Loa because they know that's how the background grows. So if your station can be adapt to that trend, it may help you to remove some of the local influences. So people do such practices, and they do some kind of preconditioning of the data before putting in the inversion, because the raw data is never acceptable in the inversion, because that will not because the raw data may not be a representative of a larger footprint. See the footprint we are looking for. The regional inversion areas are so large here. So that you are correcting for such a large domain, for example. So you need a pristine background data to represent the larger footprint, and which is homogeneous in nature in this inversion. So that's why we do some kind of preconditioning. We know it is scientifically hard to justify why you correct the observed data, but that's what we can do the best. It is some similar to we are removing the outliers, or do some kind of correction to avoid the local influences and make utilize the seasonal cycle at least, because it has information about the local biosphere. That is a good information. So let us encache it. So that's why we did some correction to achieve this. Say, for example, doing so, we corrected the trend, and some of the outlier also got removed. We come up with this. That is our justification to that.
Yeah. Okay. Yeah. Thanks, Vinu. It's a really nice answer. So Harif is asking again, maybe this is related to observation. Is there any station planned in plains near Srinagar to look at data uncertainty due to elevation, pressure differences, etc.? Maybe I can answer this.
Yogesh, you answer that.
Yeah, so Harif, right now nearby Srinagar we have not planned, but Srinagar is almost 45-50 kilometer far from our IITM campus, and we are already doing measurement using Picaro since 2015. So we have data from here, but we have not utilized this IITM data in the inversions. But it's a very good suggestion. We'll think on that. Right now we have not planned. Okay, so next question is from Dr. Prabir. He says, nice to see many analysis of CO2 flux and flux uncertainties. We hope to have better constraints on the summertime uptake. I have feeling India as a whole is a weak moderate sink. Until we constrain all seasons, the pre-monsoon release will push the India total CO2 flux towards neutral week. So it's a comment. But if you want, you can. Yeah.
That's a very good comment. Actually, Prabir is pointing towards constraining in the summer season, which he himself agrees that satellite is unable because of the cloud screening. And it is demanding more station-based data, pristine data. I would stress that point, covering the entire season. Maybe more network we need to establish, and maybe ART will help, which is sitting at the center, Bhopal, and can capture. It's a plain land, and we hope, and a tall tower. Prabir, maybe when we get that data in another 1 year, we will get a better estimate of Indian CO2 budget.
But here I have just one comment.
Yes.
Pre-monsoon in Northeast India actually works as a sink, a very good sink.
Yeah, that's true. That's true, Supriyoji. But here in our inversion, they will all get averaged out because India is considered as one whole coarse region. That is true. Such regional differences only VPR model can tell, because they have every 25 kilometer a pixel. But it's not inversion. It's an empirical estimate of with metrology. Yeah. Further, I mean, we cannot cut down the region just so much also within the global inversion, because there may be some relation among the region itself within the global inversion, and maybe Prabir only can answer that. I also not well versed in how fine you can cut the region in a. They cut like a 64 region, 84 region, and all. They do that, but there is some reasons for that I also not well aware of how they decide it.
Yeah, so that's a bit of judgment. I mean, you are already doing that. I think in the process you already learned that because you subdivided India into some part and this one. Basically, it depends on the amount of observations you have at hand, but also to give some degeneracy or degree of freedom to the inverse model so that it has more degree of freedom to adjust the fluxes. Like as you see, like if you have the whole Eurasia as a big region, it is not at all practical, right?
Yes.
So you can just by breaking them, you can see the difference in fluxes. So even the same data sets.
Yes.
So that degree of freedom you want to bring to the system. So, but then it also depends on the number of observations. Otherwise, you have a lot of dipoles and etc. Because if you constrain one region too strongly by giving low uncertainty into the concentrations, you might produce the negative or positive outside that stations. So yeah, but I think what you are doing is correct and reasonable. So yeah, basically we need more observations to go final resolution.
Okay, that's yeah.
Right.
Okay, so Chaitanya is asking, more source of CO2 in dry season is rather less fixation by the dried up vegetation and more fixation by rejuvenated vegetation during the wet season. As it is high altitude mountain station, please comment. Chaitanya.
So he's saying more emission during dry. Can you read that again one more time?
More source of CO2 in dry season rather than less fixation by the dried up vegetation.
This comment is towards that one of the conclusions you have shown in the second slide about the CNG station, SNG station.
Okay.
So I don't know. So the what exactly the more source during the dried up season?
Yeah, basically he is asking if we have a more source, it means vegetation is weak.
Weak, yes. GPP is weaker, more respiring than NPP.
Next slide.
Weaker, yeah.
I think that is what our logic.
Yeah, and wet season it is because vegetation is growing up and
if you look at the NDVI over India, even April, May is very low NDVI, and which goes by June and then max peaks at November, September, October. So we use that curve to explain this.
Next slide, sir. Could you just go to the next slide?
Yeah, this one. Point number?
Yeah, the first one. So no,
the interannual first one.
Yeah, SNG suggests more
source in the dry season. Source means more respiration in NE. That's what we say.
Yeah.
Not fossil fuel source. Okay, more respiring in the dry season and sink in the growing season. Growing means biospheric growth, not the agricultural growth.
Okay.
Yeah. That time sink is weak. So
yes, correct.
Due to vegetation, basically.
Correct.
Yeah. Thank you.
Yeah. Okay. So this was the question in the chat box. If anyone wanted to, Dada is asking, what is the prospect of making the NIST-TM model isotope pressure enabled?
I think Shamil can answer that if Shamil is there.
Yeah.
Is there any capacity to simulate isotopes, transport of isotopic species?
Shamil, are you there? Is it there in the?
But I think it's basically no issues. You can do it. Basically forward transport, and you can do the same way. Just to calculate the emissions by the fractionations. It is commonly done now. It's nothing. No difference in as such. Slight changes in thinking.
Right. Yeah.
Okay.
So one more question is there. Let me see. This is just the last question from Abdul. Why is no satellite data about GHGs available over Himalayan area when we see AIR's GoSat or any other product?
One reason is, I can show the availability of data in this one. This is GoSat and OCO2 availability. There's a number of observations per day. So we do have data over Himalayan region, especially in CO2 results, but GOSAT has stringent screening criteria. So many data get, but still in December, January, February, you see some data, GOSAT observations per day, and in September, October, November. But in the cloudy condition, we do not have. But OCO2 has a better coverage. But I don't think Himalayan region has no data. I can see some good number of observations per day.
Right. Yeah. Correct.
Yeah.
Thank you, Vinu. Yeah. Praveer, please go ahead.
I mean, much more than the plain India.
Yeah. Right.
In some season, yes, at least.
Yeah.
Okay.
Yeah. So one more, Deepshika is asking, just she has posted now, is GOSAT data, L2 data bias corrected? Data is the best option to use?
GOSAT L2 bias corrected.
L2 bias corrected data is the best option to use?
Yes, obviously. This is our work. We are using it from L3, gap filled XCO2 from GOSAT.
Right, yeah. Okay, thank you, Vinu. It was really very nice overview what I see from IITM, you and CG Kumar, and then Philip, Sajeev Philip from IIT. It was really, it shows the strength that inverse modeling is really gaining a strength. I think Praveer, you may comment more. So I think in next GHG workshop or maybe another 5-year timeline, it will be more developed, and probably you are the guide. So you can guide all this.
Yes, Praveer.
Yeah.
So no, I already passed on to you people. I think I just now only. I really enjoyed this conference because this workshop, because previous two one too much load on myself. So thank you very much.
Yeah, it was more focused on inverse modeling and observation, and now observation people are also gearing up in leadership of Chaitanya. So Chaitanya is going to do something for us.
Sure, no. Thank you.
Yeah.
Okay.
Yeah, all of you together, I think.
Yeah. So thank you, Vinu.
Thank you,
thank you for very nice, interesting talk. Okay, so we'll go for the next talk. Shamil, can you hear us?
Yes, I can hear you.
Yes. Shamil, can you please upload your PPT?
Do you see my screen?
No, not yet.
And so I will try to launch that.
Yeah.
Do you see anything?
Not now.
So how about this way?
No, not yet, Shamil.
Shamil, you need to click the open share tray. Once you click that, you get a share screen option. And when you click that, you can get an entire screen option. There you can click and share.
Okay, so I
start with open share tray.
Share. Okay, here from there, what do you do?
So you click on it, then a new window pop up.
There will be window, yes. From that, I can have some
select on entire screen. That would be the best. Then select and share.
Select
and share.
And share.
Let's wait.
Okay.
The screen, right?
Now I see that. Yes. Okay. So then I
yes, it's coming up.
Do you see something, right?
Yes, it's coming up. Wait, hold on.
Okay. So then I can try to.
Yes.
Yeah. You go to full screen slideshow mode. Then it will be fine. Very good. It's up. Yeah.
This one you see, right?
Yes.
Good.
We can see.
Good,
can you just change one slide so that we can see each slide is changing? Yeah.
Yes.
Okay.
Yes. Changing. Okay. Nice.
Okay.
So.
Okay. Yeah, Samil, just hold on, because I have to give a brief overview about Shamil, and because Shamil is a very important person for at least for us at IITM, and then the model development and these things, Shamil really helped a lot. And Shamil is involved basically from base to carbon cycle research in India. So Shamil is a very tall personality in carbon cycle research in the global community. And even his biodata, I don't want to go because it's a really huge achievements. So only I will tell you, so he has almost 400 publications and almost 45,000 reads and 12,000 citations. So you may understand the Samil's contribution to the carbon cycle community in the world. And Samil's basic education is from Moscow Institute of Physics and Technology. So he studied physics, and then he joined Nice in 1990 as a visiting researcher. And then in 2000, he joined Japan Agency for Marine Earth Science and Technology, Marine Earth Science Technology. And again from 2005, he joined Nice as a lead scientist as a section head in 2011, and he's continuing as lead. So basically, he is an expert in inverse modeling of CO2 and methane surface fluxes in global scale. So these are the Samil contributions, and then basically he do not need any introduction. But I, as a customary for the young scientist, I told about Shamil, and we all welcome Shamil, and we really thank Shamil to accept our invitation to give a talk on this workshop. So Shamil, please, we request you give your lecture.
Yeah, thank you very much for introducing Yogesh. And okay, I will start my presentation about global high-resolution greenhouse gas transport modeling and flux inversion. And I will report today the work that mostly contributed by myself and my group colleagues Rajesh Janardanan and Finjuan Wang. And the topic I want to start with is why do we want high-resolution inversion tools? Most recently, the changes in the inversion landscape are caused by the Paris Agreement. With Paris Agreement, we have a change that we are addressing now more closely the principle of the greenhouse gas fluxes, the anthropogenic emissions, rather than trying to do some small optional approaches like trading small reductions. Then we have to go for big reductions in anthropogenic emissions of greenhouse gases. So in that context, we see there is already some development in many countries on using atmospheric observation to study the emissions, anthropogenic emissions at national scale. For example, in Switzerland, UK, and other places, we see very much operational research on doing verification of national inventories. Then we see that this is done by high-resolution transport modeling, and mostly Lagrangian. So here I can show some references to papers that work on regional and national scale inversion. And you can find that in most cases, this is done by high-resolution Lagrangian modeling because this is convenient computationally to implement and do transport rather at low computational cost. For example, in case of verification of UK national inventory for methane, the pictures here you can find in UK National Inventory Report. This is work is based on building a network of the observation sites. Then with this network, it is possible to observe the impact of emissions around the UK with several stations. And then we can see the time series where you see the impact of local emission and background concentration, and again, local emission and background concentration, and see the difference between this. It can be simulated with a transport model in backward mode and do inverse modeling and then compare to the inventory for different years. And recently it started to match more closely. And well, before there was a discrepancy between inventory and inverse model. And this inverse modeling was continuing for almost 20 years now. So here is a setup for the emission inventory verification for Switzerland, where you have a network of ground-based observation plus mountainside they have in Jungfraujoch Observatory. So they have the high-resolution inventory of methane emissions, and then they estimate posterior. And they are much between the posterior estimate and national inventory is pretty close. The international collaboration on this verification is now coordinated with the WMO, Integrated Global Greenhouse Gas Information System, and they produced the science plan where they propose different scales of the approach depending on capability of different countries. So it can be based on few sites and maybe extended to more sites depending on the possible target. Then for India, for example, there was an attempt to do the validation of the inventory without using many ground-based observations, but using GOSAT. The group of Matt Rigby, the Ganesan et al. Published a paper where it shows that the emissions, anthropogenic emissions in India can be estimated to be very close to the national reporting that national report said about 20 million ton of methane, and their estimate was around 22. But actually, our paper by Rajesh Dhanardanan showed about 24. But on the other cases, many inverse models estimate anthropogenic emissions higher, like similar to Edgar of 30 megaton or even higher than that. So there is still some discrepancy that have to be dealt with. See a picture for Europe, for example. You see into comparison of the different inversion for Europe of methane, and Bergamaschi et al. 2018. You see there is only one model that is giving numbers close to the inventory here in a black line, while the Edgar estimate is higher than the sum of the national reports for Europe. And this discrepancy is there that the models often give higher than Edgar. The national inventories give lower than Edgar, and many models do not produce as much as the inventory, but they show more than that. So there is a discrepancy. Even if you use a high resolution transport model like STILT or COMET, there is some impact of the inverse modeling algorithm. So there should be more research in that direction. When you go back to CO2, then there is a interest on trying to understand how much the sink we have in the biosphere, terrestrial biosphere on a country scale. And we know there is a big terrestrial sink, but it's difficult to say how it is distributed spatially. And one problem we have with transport modeling is that the productive biosphere and population very often overlap. Then you see that in China, in US, and in India, in Europe, everywhere. So maybe there is a way to improve the estimation of the biospheric fluxes too by doing better transport of anthropogenic emissions plumes. And I show here the simulation made by FlexPart and with ODIAC emissions. So you see the very distinct plumes of the CO2 that emitted by population centers and large power plants. So next slide, I want to present our effort in doing the estimation of the biospheric sources and sinks using high-resolution inverse model. And the paper that I'm introducing is published in ACP. It's called the High-Resolution Inverse Modeling Technique for Estimating Surface CO2 Fluxes based on NISTM FlexPart coupled transport model, and it's a joint. So, okay, in this model, we first have to develop high-resolution prior fluxes. So fortunately, we have high-resolution fluxes already at 0.1 degrees resolution for biomass burning from GFAS and from the fossil fuel emissions for ODIAC. But for biospheric fluxes, at that time, we didn't have good biospheric fluxes at high resolution, so we had to develop a mosaic approach by simulating the fluxes for the multiple vegetation types, so 16 type mosaic at 0.5 degree, and then use that multiplying by fractional coverage of each vegetation to develop the high resolution flux model. For ocean, we don't develop high resolution, but I think it is now possible to do high resolution ocean flux modeling because of high resolution reanalysis, like there is FNOC reanalysis and others, but we use lower resolution assimilation by Vino Valsala and just interpolated to higher resolution. And our transport model combines NISTM at 22.5 degree and 32 layers with the FlexPart. And FlexPart is simulated by 2 to 3 days time and is coupled to NISTM exactly the same time at 0 GMT. So we have a combined simulation of CO2 that combines low resolution background and high resolution impact of near field fluxes. And then about the theory of FlexPart, it is good to check the proof, how to prove that the backward transport with FlexPart backward simulation is equivalent to forward and actually also to adjoint. In fact, there is a good literature on that, and especially I would recommend this paper by Ordan and Talagran, and they published in 2006, and there are several papers they refer to, and they discuss in detail how do you go into the parcel and prove the symmetry of atmospheric transport against time dimension. So the idea is that you can simulate sensitivity of the observation at some point to the past history of atmospheric transport along the trajectory by reversing the transport backward. This is very useful for simulating transport by backward simulation of flex part, because in forward simulation you can only produce the grid fluxes, and this is not efficient computationally. But in backward transport you can simulate event, and this is very computationally efficient, so you don't have to simulate a whole domain. So this is important theoretically to understand how is a backward transport happens and why it is possible to use backward transport. So our configuration of flex part is that we use 1.25 degree JCDAS, GRA 55 meteorology, and calculate the flux footprints at 0.1 degree. But in later version, we try to use a high resolution meteorology, for example, era 5, like a quarter degree resolution, but this is more recent development. And when we simulate forward, we see that we can resolve the synoptic scale variations quite sometimes successfully, but not always. And then there is a mismatch here that for shown in a plum is simulated forward with prior fluxes. We have to convert it with adjust with inversion, adjusting the surface fluxes to match with observation in blue here. This is the setup of the observing system we use, and we use the OPSPARC data set. And here is some short introduction of optimization technique. We heard several times already, and the specific point of this research is that when we calculate fluxes at high resolution, the covariance matrix for the fluxes is should be designed a little bit more specifically for high resolution case. The normal approach in data assimilation is to make some kind of the function that have the non-diagonal elements of the covariance matrix for flux corrections to be declining as exponentially with distance, so with a distance of like 500 kilometers typically. And for high resolution case, the design of this matrix is mostly done in ocean assimilation systems by applying implicit diffusion operator, because implicit diffusion is can calculate the impact or multiplication of matrix by vector using few operations per grid point instead of, and this number of floating point operations grows linearly with the vector size. Then it is very convenient for high resolution. So we verify this application of implicit diffusion, and here there's a picture that shows that it is very symmetric against the distance from the pole. Whether you put the some amount of flux in the equator or mid-latitude or on the pole exactly, you get exactly same amplitude of the function. So it is very convenient to use implicit diffusion for estimating flux covariance, and is practically a smoothing function for fluxes. So after that, there is an interesting topic, how to estimate uncertainty. For that, the one popular technique is to estimate the singular vectors of our transport matrix, and then we can apply the iterative technique to estimate singular vectors and then estimate uncertainty. So we can estimate posterior uncertainty by applying the iterative technique that produce a set of singular vectors for this transport matrix. Although this dimension is very large, but estimating several vectors is quite possible. Well, fluxes actually are estimated by a more quick technique, which is quasi-Newtonian optimization method, like LBFGS. And there is a very popular software, M1QN3. Then it is producing the a minimum of cost function, finds a proper flux correction by, if you can calculate the derivative of cost func, which is in our case is this function. For what is important here, you have to have a joint of the transport model to calculate that derivative. After that, the optimization software will find you the minimum after many iterations. So here's how your flux correction look like. You see, you can have the flux corrections weighted by the uncertainty field, which is controlled by MODIS GPP for this case. And the resultant posterior fluxes will still have this high resolution structure. And this shows how the cost function declines with a gradient. It is declining more or less exponentially with every 10 iterations here. It declines by some more than 2 degrees of amplitude, and can continue declining if you need to improve the minima to the more higher accuracy. This is a presentation of the match between the observation and fluxes. And here you can see that very small variations observed in Antarctic station shower can be reproduced by model because of this Lagrangian transport provides you with ability to simulate the very fine variations in time and space. So here that's some plots for multiple stations that show the match between model and observation. So this plot shows RMSE for forward model in blue and optimized model in red, and green is a carbon tracker. So sometimes our model is doing better than carbon tracker, and sometimes the other way, carbon tracker can do better work. And so the places where we can do better than a low resolution model is mostly coastal stations where the high resolution is useful to distinguish between oceanic and terrestrial impact. For other places, the performance is very similar, and very often carbon tracker even does better. So at this time, for as expected for the biogenic fluxes, the advantage of high resolution is not very visible, but it can change when we shift to doing anthropogenic emissions. And specifically for some stations, we can see here, and also here, the Cape Rama is a problem for both stations, like Cape Rama is here. Then both carbon tracker and our model have pretty large the uncertainty of the RMSE, and also bias here for Cape Rama here is pretty sizable on both sides. The bias here is shown in one direction just to make plot compact is absolute value of bias. And we see for both our model and the carbon tracker, we see sizable bias here. So this is still a problem of doing better work with filtering and the prior flux definition. Say next thing is look at the posterior fluxes. We see that we can have a large deviation from prior to match the observation, and our posterior is often very close to the flux estimated by carbon tracker here in blue. Now we go to methane. For methane, here I show the total column simulation with Lagrangian model flex part in forward mode. That is very convenient to simulate the 3D structure, and even more convenient to simulate 2D structure like X-methane. So here you see that there are many locations, especially around the cities, where you see distinct plumes emitted by the anthropogenic sources, which have to be resolved by transport model. And in the paper that I present here was written by Rajesh Janardanan in remote sensing. Then it is addressing country scale analysis of methane emissions with the high resolution inverse modeling using GOSAT and surface observations. The observations we use are coming from World Data Center for Greenhouse Gases and the GOSAT data for the period of 2009 to 2018, I think. We use the set of prior fluxes, which is EDGAR for anthropogenic emissions, VISIT for wetland and soil sink, and GFAS for fire and other minor fluxes like termites, ocean, and geological emissions. And also we use OH fields, monthly 3D fields from Transcom, same as Transcom, that comes from Spivakowski et al. We remap the visit wetland fluxes from 0.5 degree resolution to 0.1 degree using maps of wetland area, global lakes and wetland data set, which is maybe not very perfect in some places like we found that's too crude in India or Finland, but it's a good approximation for wetland distribution anyway. So the uncertainties we assign to fluxes is 0.3, 30% of EDGAR emissions and 50% of visit emissions. So we use GOSAT data. Then for each scan, we use the data separately, and we estimate the bias of the GOSAT data against model in like latitude bands, making it like in 5 degree bins. And you see here there is some trend in the bias, and there is the trend depends on latitude and month, and there is a very regular pattern in that trend, and the latitudinal distribution shows maximum bias in low latitudes. The flux corrections are made by estimating the basically scaling factor to fluxes, which is can be expressed in percent of original emissions. Here we see the difference between original and corrected emissions for anthropogenic EDGAR component can be between like 0 to 20%, and similar amount of correction we can see for wetlands. This is a posterior fit estimated in Rajesh's paper for different sites. We see that for many background sites, the fit is good, and we can see a good match. And for some places, it's not always easy. In that version specifically, it wasn't easy to simulate Canadian fluxes. We see some difference in India for some season, but mostly it is not doing bad job. For background sites, it's more or less matching well. Now, even here in Japan is a Ryori station. Some season is difficult, but most of the other thing is working well. While for CO2, actually in summer, because it is very close to the continent, it's difficult site. The advantage of doing this high resolution is that we can construct the fluxes and flux corrections and high resolution grids. So see here, you see monthly fluxes for total methane emissions. And here it is the same set of fluxes, but showing anthropogenic fluxes for more in a closer zoom. So our estimates show that the methane emissions are very high in China, the US, and Russia, and other big emitters. And important is to check how it is doing the emissions against the national inventories. We use national inventories as a prior here. We correct EDGAR by national inventories and then compare that to posterior. Well, the differences are actually within uncertainty range. The uncertainty range was reported in Finjong Wang paper in 2019, was estimated by the Monte Carlo method proposed by Frédéric Chevalier, where we can randomly perturb the national fluxes by amount of uncertainty, and then calculate the spread of ensemble of 5 inversions. And then we get uncertainty here. So we see that the difference between the country scale fluxes and the estimated posterior and prior and national inventory, then we have the differences here for the anthropogenic component, and this difference is normally within the range of the uncertainty. So it is a good sign. Now, another thing is that for the anthropogenic posterior for India, we don't get big discrepancy with the national inventory, which is around 20 megaton. We get 24. That is a reasonably good match, because in many other inverse modeling exercises, the flux for India is reasonably high. But it is also depends on the prior in our case. So here is a validation against the observation, the aircraft observation over India provided by Yogesh. Then the red line is estimate with forward simulation made with prior fluxes, and green one is observation, and the optimized fluxes show the blue one, and they are very close to the to the optimized model. And these observations are not used in the inversion, only GOSAT and other ground-based. So this is independent verification. One interesting thing in observation, there is a small increase in upper part, which is probably transport of methane to upper troposphere to some area below the tropopause, where we can see enhancement, which is not reproduced by models. So this says maybe vertical mixing in the model and penetrative convection is not strong enough. So this is probably all we can say today about this model output. We are still continuing to improve and working on model development further. And I want to introduce a little bit some other topic about that says on value of high resolution simulation and impact of high resolution for simulating the satellite observation on anthropogenic emissions. We found that doing just the Lagrangian transport without Tellurian, we can see a very good correlation, and we can do regression of the simulated enhancement by GOSAT and FlexPath simulation, GOSAT observations against FlexPath simulation for CO2 and methane. So there are two papers by Rajesh in JRL in 2016 for CO2 and remote sensing 2017 for methane, where we see a good match between the model simulation and the GOSAT local enhancement simulation against observation. But to do the comparison, we bin the observation by simulated enhancement. So for average of the all observation in this, when the simulation is within this from 2 ppb to 4 ppb, we can make average and see that for large number of observations where we take the observation of a whole globe, we see very linear and very close to one-to-one line. So this is a good indicator that doing the high resolution transport of anthropogenic tracers, we have a good match with satellite data, and this is a powerful tool that should be explored in the verification of national inventories. Well, a small comment about recent development, where we what we do with transport model after publishing those papers. And the one effort is to use high resolution meteorology by ERA5 reanalysis, where we take the data interpolated by ECMWF at 0.62 degrees at original 132 levels at hourly time step. And then we can calculate the mass fluxes for our model at different resolutions. The classical is 2.5 degree and 3.475, and also 5 degrees, 7.5 degree, and 10 degree. And then we can simulate the transport a little bit better than we did with a lower resolution wind. We verify the model against the SF6 simulation and radon and other tracers according to Transcom Age of Year experiment by Kroll et al. And we see that our performance is very close to the settings set by this experiment. So it is we had some progress for future developments. And also we do some model improvement in the data storage for the flux responses, and that would allow us to improve the resolution of fluxes to maybe 5 kilometer or 3 kilometer in future. So as a summary, I can conclude that we have achieved for CO2 inversions. We get a very similar mismatch to carbon tracker, similar flux seasonality, and a little bit better transport in some marginal background stations where there is a coastal site on a contrast between land and ocean. For methane emission at country scale, made with GOSAT, we are in more or less good agreement with national inventory reporting. And the general conclusions are follows, that the ability to quantify the natural anthropogenic fluxes for CO2 and methane are important for climate change mitigation. And but until now, low-resolution Illyrian models were applied to understanding natural fluxes, where anthropogenic emission plumes are producing interference, preventing use of the many continental observations. So the anthropogenic emission estimate had to be done using regional models, so that is not very convenient for producing global flux reanalysis. So we develop a computationally efficient approach for inverse flux modeling at fine grid scale of 0.1 degree globally. High resolution global inversion is still memory and CPU intensive, but introduces large savings in computing cost of full high resolution Illyrian model. And we hope that developments provide capability to separate anthropogenic emissions and other surface flux categories as a step towards high resolution inverse modeling of anthropogenic emissions of CO2 and other greenhouse gases in a global scale, addressing the needs for verifying effects of emission reduction measures. But one final comment I'd like to make is that we actually developed a guidebook in NIST for use of satellite greenhouse gas observation data, where we summarized different efforts, not only inverse modeling, but also other more simple approaches. And you can access it in this site at NIST web page. Thank you.
Yeah, thank you, Samil. It was really a very insightful talk, and then it's really very helpful to the young researchers and to all of us. And without any delay, I wanted to just post questions to you. So first question is from Pramit. How do you account for the peatland in these models? Is there a separate land use change class, or it is considered in wetlands?
The peatland emissions are simulated by VISIT model. So VISIT terrestrial ecosystem model simulates the fluxes of CO2, methane, N2O. So we use that simulation as a base. It is not perfect, but can be used as a good first approximation. And as I mentioned, in some places, the problem is the land cover data that goes to as an input is a combination of global lake and wetlands data set and also some remote sensing inundation data that also needs some improvement and verification. And sometimes we commend that, especially in India, fine resolution wetland and freshwater emissions are desirable.
Okay. Yeah. Next question is from Dr. Prabir. It's a very important question. A lot of new directions, okay, in your talk. My question is, when you show animation of methane from Lagrangian model, everything is like plume. So is the background methane considered? Also for CO2 fluxes, you are not showing ocean fluxes. Are the ocean fluxes not corrected?
Actually, the simulations I show only an anthropogenic part, which is basically corresponding to the in the observation time series. It corresponds more to the spikes where you can see over background. That is more difficult to adjust with the model than the baseline. But baseline adjustment by inversion is easier than adjusting those spikes on roughly speaking. So that's why I showed them separately. But ocean fluxes are, of course, corrected and adjusted, and especially you cannot get fit in southern hemisphere like in for CO2 without adjusting ocean fluxes, like, for example, here in Antarctica. This seasonal cycle without adjusting ocean fluxes is not possible to get.
Yeah, okay. Okay, next question is from Harif. He's asking, Southern Ocean is reported to be a fast changing source and sink characteristics. Is it important to include in the global scenario?
Sorry, can you repeat that?
He's asking, Southern Ocean is reported to be fast changing source sink characteristics. Is it important to include in the global scenario? I also don't know what he wanted to ask. Anyway, yeah, so next question is from Pramit again. In Nordic countries and UK, peatlands are heavily cultivated and they can have very different emission patterns compared to the unmanaged peatlands. Does the visit simulation capture this?
Probably not. Not that much detail. So the difference between for example, managed peatland and the natural peatland, I have to check how the land use is being accounted for in visit model. Of course, this is important because in say Southeast Asia, a lot of peatland has been drained, and then it is probably taken into account as average water level setting for a region. So I have to check about detail on that.
Yeah. Yeah, Vinu is asking, this methane flux data is available publicly?
Sorry?
He's asking, is this methane flux data available publicly?
Not yet. We are trying to make it available to download from NIA's website. So, but we are working on that.
Okay.
Yes, on request, I think there is a chance we can distribute to people who want to use that as a collaboration. Yes, because this is intended to be, intention is to use publicly. Yeah.
Yeah, yeah. And Shamil, just my question is this 0.1 by 0.1 grid, this is for methane, so for CO2 also it is there?
Yeah, for CO2 as well, we do 0.1 by 0.1. And as I mentioned in, there is a page about recent development. There is we use observation-based prior fluxes by terrestrial vegetation. And this made by Zheng et al. 2020 scientific data paper, which is made by, is like Fluxcom made from fluxes. So we have a reasonable set for prior in CO2. So it is, I think, safe to produce inverse model estimate at this resolution.
Yeah. Okay, thank you. Dr. CG Kumar is asking, in high resolution regional inversion, how point sources are addressed?
Point sources, for example, when you use Edgar emission at 0.1 degree as a prior, and also the prior uncertainty. So the inverse model estimates the field of scaling factor to that Edgar field. This one. So this scaling factor is applied to high resolution Edgar at 0.1 degree. That's how you correct point sources and non-point sources by the same factor. Well, of course, in a more revised system, we can separate some categories, like, for example, for methane, we can treat separately gas leaks and waste water treatment and now the landfills. These are point sources, but could be different categories. But anyway, the idea here is to use a scaling factor at low resolution and the emissions themselves at high resolution. And this is a way to treat the point sources.
Okay. Yeah, thank you. I think it's very good information. Yeah, Vinu is asking, the uncertainty matrix has non-diagonal elements at exponential of x square by r square. How important is this in non-diagonal part?
Yeah, do you mean the diagonal cycle or what? It's
Vinu, yeah, can you?
No, your uncertainty matrix has a non-diagonal element as an exponential minus x square by r square. How important is this non-diagonal part in the inversion?
Yes. The idea is that if you don't have the non-diagonal part, your scaling factor will not be that smooth as it is now. It will be very spotty and noisy.
Oh, okay. Thank you.
So the spatial correlation means is that you assume that fluxes in nearby places are not independent, but they are changing similarly. So the flux observation over this path of the transport model plume is applied over large area. So you assume if you know the flux correction over this place, over this city, a city 100 kilometers from that place will use the same flux correction.
Okay. If anyone has any question, they can unmute and ask, because we do not have any question in the chat box now. If not, then let us thank Shamil for giving a fantastic talk. And now this is end of this session. And this session we had 3 talks from Dr. CG Kumar, Dr. Binuval Chala, and Dr. Shamil. So all the 3 talks were really very insightful, and then a lot of results were shown. And I am very sure that all the young researchers who are attending, and also all of us, will really benefit to them. So this is all from my side, and then I give mic to Venu for further proceedings.
Okay, thank you, Yogesh, for chairing this morning session excellently, and it was nice chairing. And now, before we disperse, few changes to announce. One is that Dr. Yogesh's talk yesterday, due to technical difficulty, day before yesterday, we could not take. So we can accommodate that after the plenary, after the keynote in the afternoon. Yogesh can talk. And there is also a change in the hands-on training. Today's hands-on training, the candidates planned, there are having some COVID issues there. Their office is kind of cautious shut down. 4 cases reported in last 2 days. So there may be a change in the hands-on training today, but we are finding a replacement. So we will update you during the post keynote talk in the afternoon session. So Yogesh can speak after the keynote for your talk, and then we will. So there will be a slight shift in our schedule of panel discussion also to 30 minutes at least, minimum 30 to 45 minutes.
Yeah. Okay.
Yeah. So please adjust the shifting in time. Yeah.
Yeah. Yeah.
So we'll regroup up at 2:30 today as we planned.
Yeah. Yeah.
Okay.
Okay. Thank you. Thank you.
Thank you, everyone. Yeah.
Great, fantastic. So see you again.
See you again. Bye.
Hey, Pravir.
Hi, Paul.
Hey,
Nice to see you. Yeah.
See you too.
Yeah. Great.
Can you hear me okay? I've got my microphone here. Is it clear enough?
Yeah,
Yes.
we can hear you.
Very clearly.
Okay, good.
Are you at office or at home?
We're working from home now.
Yeah, again.
Yeah, again.
But sometimes you go to office, right? Sometime.
Sorry, say again?
Sometime you go to office.
I have been, but I think now we've been encouraged to work from home as much as we can.
Yeah. Also, in your holiday seasons are coming, and you are.
Yeah, this is my last day, so I'm taking off next week because I'm really tired, and I decided I would take a week off before.
Oh, we are lucky.
Mm-hmm. Have you got all of next week?
No, we are done with this week.
Oh, right. Oh, yeah. Okay.
Yeah. Today is
So
the
this
last
is the last
day
thing
and
for you to do today.
last few hours.
Yeah. Yeah.
Good.
So is your son back home now?
He's coming tomorrow.
Oh, okay.
Hopefully he can arrive. Okay.
Has he had much face-to-face teaching at Imperial?
He's going to college almost regularly for
okay.
work. He's in the final year, 4th year, so a lot of projects. Yes.
I know, it goes past really quickly.
Yes, lots of project work, so yeah, he has to go to office.
What are his plans after he graduates?
He'll talk to you, I think.
He'll talk to me.
I mean, somewhere, because maybe he'll continue studying somewhere else.
Yeah, okay.
Looks like you want to be a student.
So he wants to do a PhD?
Something like that, yeah.
Okay, that's good. Good.
Yeah, you can try to put your PowerPoint and.
Yeah, I can share my PowerPoint. I'm going to turn my camera off for now if you want.
Yep, you can.
Can you see it?
Yep. You can go to the presentation mode.
Oh yeah, that's a good point. Yep, I'll do that. Just let me know when to start.
Yes, it looks all good. So Supriya will now take over.
Yes. So we can start now.
I can start now.
Yeah, we can start. Yes. People will keep coming, but maybe we can take 2 minutes and then start.
Sure, just let me know when you want to start.
People are still logging in after the lunch break, so 2 minutes would be good. Yeah, thank you.
Okay.
Hello.
Yeah, Supriyo, please start
yes,
now.
maybe we can start now.
Yes, please.
Okay. Good afternoon, everybody. Now, this is in this post-lunch session, we have a very distinguished speaker, Professor Paul Palmer. I will give a brief introduction about Professor Palmer. He is a professor of quantitative earth observation at the University of Edinburgh. He received PhD in physics from Oxford University in 1998. His area of research is vast, including modeling atmospheric chemistry, measuring and modeling biogenic VOC fluxes, inverse modeling, and satellite remote sensing. He has published more than 150 research papers. He has accomplished over 50 projects. He has received various prestigious awards, including Philip Llewellyn Prize, Royal Society Wollstonecraft Research Merit Award, and many more prizes. So I would request now Professor Paul Palmer to deliver his lecture on atmospheric modeling of greenhouse gases.
Okay, well, thank you very much for that very kind introduction. Can I just check again whether you can hear me?
Yes, sure, we can hear you.
Okay, that's great. Okay, well, thank you very much. I guess you've enjoyed almost a week of lectures. And in some respects, what I'm going to be talking about today will build on a little bit what other people have done, sort of maybe look at how models are built and what do we mean by models. And I guess some of you have already sort of thought about this already because you've had some wonderful lectures from your lecturers. So this is about atmospheric modeling of greenhouse gases, and in particular, this is the breakdown of the talk. We have I've got a lot of slides here, and I think I'll just cut off when we run out of time, which I believe is about 45 minutes. So if there's any questions you have, just post them in the chat. So I'm going to start off with why you should care about atmospheric greenhouse gases. I'm not going to spend a huge amount of time on this because I hope that you already know why they're important. I'm then going to talk about why, what do these measurements tell us about greenhouse gas emissions and uptake, and then go on to talk about what's the purpose of atmospheric models. Now, for most of the material I'm going to be talking about today, I will focus on CO2, but I will come and go with methane as well, because methane is a great example of some of the concepts I'm going to discuss in this lecture. So this is a very simplified picture of the carbon cycle, the contemporary carbon cycle. Now, these numbers are taken from the Global Carbon Project, and it's a very simple schematic. We've got various fluxes in and out of the atmosphere. So the atmosphere accumulation is about 19 petagrams of carbon per year, sorry, 19 CO2 per year. And so 1 petagram of CO2 is about 1 billion tons of CO2. Now, what's driving that is primarily fossil fuel combustion. So there's quite 34 petagrams of there. And we also have deforestation. Now, roughly speaking, about 50% of the CO2 emitted into the atmosphere stays in the atmosphere. The remainder is taken out almost equally, but not quite, by the land uptake. So we have photosynthesis, and some of that carbon's being stored in above ground biomass and below ground biomass, and of course ocean uptake. But basically what the atmospheric CO2 that we'll see in a minute is really a balance between these fluxes. So the atmospheric CO2 is growing, and it changes from year to year, and that's a reflection of different the fluxes, all these fluxes that change from one year to the next. And many of these have very large uncertainties, particularly deforestation. Deforestation's got a very large uncertainty, and you've seen all kinds of reports in the news about Brazil increasing, decreasing, stopping deforestation, various things like that. So from year to year, this is a very large, sort of significant but uncertain flux, for instance. And places, land uptake and ocean uptake, these are also responding to some extent to the climate itself. So there's also a large variability here. Now, this is another figure from the Global Carbon Project. It's a very nice picture in terms of, gives you a sort of a a sort of very summary picture of all the different sources and sinks as a function, as a function of time. So this goes from 1850, so this is what it has on the x-axis, 1850 in the x-axis, and then we have CO2 fluxes on the y-axis. The figure on the left, that describes the flux per year. So for each one, you just read off this is the value. So in any 1 year, we've got more or less a balance. Well, we assume there's a balance between fossil fuel emissions, and we have land use change emissions. At the start of the end of the 19th century, most of the fluxes into the atmosphere was driven by land use change, and we only get after the Industrial Revolution do we get sizable increases from fossil fuel emissions, of course. So all the emissions, the net emissions, are on the above this zero line. Now below the zero line, these represent sinks, lost processes. These are things that are taking CO2 out of the atmosphere. So we have the ocean sink, we have the land sink, and of course we have atmospheric growth. Okay, so I guess that's not really taking it out of the atmosphere, but it is responsible for. It is growing in response to the emissions at the surface. So that's basically the final resting place of the CO2, at least temporarily. Now, what you'll notice here is that so the dashed red line here, this is a reflection of this. Basically, is symmetrical about the zero line. Okay, so this dashed red line is basically following that red line on the top above zero. Okay, and the purpose of this is really to show you that our knowledge of the sources above zero and the sinks, the loss processes below zero, are out of balance. Okay, we don't know necessarily why some years, you can see there's gaps here, right? So we don't know what's balancing out the carbon cycle. There are things in the carbon cycle that they're not balanced essentially. So there'd be instances where you'll see that the total loss processes are larger than all the sources. So that would lead to a decrease in atmospheric CO2, and there'll be instances where the sinks are much lower, and so you get this rapid increase in atmospheric. There's an imbalance. Okay, so the sources outweigh the sinks, and that's really just a reflection of our uncertainty. So we're missing effectively some understanding of some processes in the Earth system, which would balance out our understanding of what's going on here. The figure on the right is the cumulative emissions in their partition, and I won't go into that anymore. It's less interesting, this year-to-year variation, but what you can see quite clearly is that in all of these cases that the cumulative emissions and the cumulative loss process are increasing with time, unsurprisingly. Now, one thing that when I first gave this lecture a while back, it really is quite a surprise that given the importance of atmospheric CO2 and other greenhouse gases, that we've only just started measuring them. We've known about their impact on climate for hundreds of years through various studies led by a range of very famous scientists. But it was only since the 1950s, in the first geophysical year, that the atmospheric CO2 was started to be measured in a very accurate, precise way. And the situation for methane is a little bit worse. So we only started routine systematic measurements in the 1980s. Now, the link between greenhouse gases and climate, as I said, we've known this for a very long time. What's the problem we have right now is that reducing emissions of greenhouse gases, because they're tied to various economic activities, it's become a political issue. And we've seen in COP26, people don't want to reduce their emissions because it will have implications for economic output of their countries. Okay, so that's the big problem we have right now. So the science is completely solid, but reducing emissions is now a political issue. So really, we're only getting to grips with issues that should have been addressed decades ago, if not long before that. Now, the guy that put together the first measurements was a guy called Charles Keeling, and we'll come back to the measurements that he started collecting was in Mauna Loa, which, as you can see, that's that star here. It's in Hawaii, in the middle of the Pacific, and he collected about, this is the measurements of 1960. This is some of the earliest measurements he collected, and there were two immediate discoveries. Even after a few years of collecting atmospheric CO2, there were two things that were completely just completely changed our understanding of atmospheric CO2. So the first thing was that we saw this large-scale seasonal variation. Okay, so we're seeing these ups and downs. So this was the first evidence that we were seeing natural seasonal breathing of the planet. So we saw these photosynthesis and respiration fluxes which occur on seasonal timescales. That was the first time we'd realized we could actually, this kind of activities were observed on a global scale. The second thing, and perhaps the more important thing, was that this is the first time we'd really understood the fact that humans were having a very significant effect on these greenhouse gases, and atmospheric CO2. So the slight rise in atmospheric CO2, he linked immediately with the combustion of fossil fuel. Okay, so previously people thought that the amount of CO2 that people were emitting through industrial activities wasn't large enough to increase atmospheric CO2. So his measurements were key in throwing that idea out of the window. Now, this is what we've got here. So this is the natural flux, just building on what we've talked about. So this is the natural biosphere. We have trees and we have grasslands. We have net emission, which are respiration fluxes and photosynthetic fluxes of CO2. Now, much of this carbon gets converted. Sorry, the carbon gets absorbed. It gets converted into above ground biomass. So things like stems and stumps and branches, bark, seeds, everything that you would associate with a growing ecosystem. And then some part of that carbon will also be stored in below ground biomass, so roots, soil, organic matter. And it's really important to have that whole picture of what's going on. Now, this whole picture is also sensitive to climate and human intervention. So things like deforestation, large-scale droughts that we're seeing over the Amazon basin and places over Africa, this will have implications for the carbon being stored in all these different components. Now, when we look at the time series of CO2 in the atmosphere, so this is a more recent picture of what we now call the Keeling curve. And it's very much an iconic data series now. We've got it for 60 odd years or so. So what we have here is, this is the most recent period, so 2017 to 2022, and we've got parts of million CO2 on the y-axis. Now what you see here, so the red line, these are, I believe, monthly values which NOAA produce on a regular basis, and then the black line is the deseasonalized time series. So they've just removed the seasonal cycle. So you can see there's a steady increase in CO2 with time. So this can be attributed to combustion. The seasonal cycle, this is basically the natural biosphere. So this is the primarily the land biosphere, but there's also a seasonal cycle associated with the ocean uptake as well. Now there's a lot, so the zeroth order model, and we'll come back to what a model means in a moment, but a zeroth order model is an annual linear increase of fossil fuel combustion superimposed with a sinusoid, okay, so to do with the land and the ocean biosphere. And that is your zeroth order. That's basically, if you were to take that model, those two parts of that model would be, you could predict CO2 reasonably well. There's some differences, of course, but that's not a bad way to start modeling atmospheric CO2. Now, so the mean annual CO2 growth, this is what we're seeing on this black line here, is about 2 ppm per year. Okay, so it's about 15 times 10 to the 15 grams of CO2 per year. And just to put that into context, if you were to, the global human biomass is about 0.2. So we're talking about orders of magnitude, well, an order of magnitude more CO2 being pumped into the atmosphere than the entire mass of the human population. Okay, so it's a huge amount of CO2 mass that's going into the atmosphere every year. Now, what we'll see, there's a lot here, and I won't spend too much time on this today. But what you'll see is there's some differences in the depth of the minima per year, and there's in increases in the maxima. There's also differences between these points here. Basically the shape of the sinusoid, or the shape of that seasonal cycle, changes from one year to the next, and that reflects all kinds of things. So it could reflect, so El Nino, for instance, would impact it dramatically. There'll be less uptake in some places, so you'd get a smaller dip in the seasonal cycle, and you might get a larger increase in the maxima. So there's all kinds of clues in the data set will give you information about the behavior of the terrestrial biosphere, and that's indeed what people have started to look at. Now, again, just to put this into context, this is the large-scale, the year-to-year variations in atmospheric CO2. So you can see here is the year from 1960, from pretty much when Charles Keeling began his measurements, to more or less present day, and then we have CO2 annual mean growth rate. The lines here, these black lines here, these denote the decadal mean. Now, some of these features we understand, while others clearly are not unexplained. We don't fully understand what's going on in the carbon cycle. And so when you see papers published by all the prominent authors that give you some sense of at least provide some information about whether we understand the carbon cycle, that's just sort of, you're just looking at bits and pieces of the carbon cycle. We do not have a full comprehensive picture of the carbon cycle. We do not know more or less where some of the carbon is being taken up. We do not fully understand why carbon, the atmospheric growth rate, changes as much as it does from one year to the next. I'll give you any reason why it's becoming more complicated as we move. So we're now trying to make the model more complicated. Very simply, so this at the bottom, this might be something that you're looking at in the atmosphere. So it looks like quite a complicated observed variation in CO2 or methane, doesn't matter. And the point of this slide is really just to give you a sense that you can get this very complicated picture of atmospheric CO2 doing some very simple things. So the first thing is we add an invariant seasonal cycle. This might be, simply put, this could be just the biosphere without any perturbation due to climate. So it's basically breathing in and out every year. So you have respiration and photosynthesis every year. Now, what you can do is you can start to add all kinds of anthropogenic and natural factors. So you might have, in this case, an accelerated oscillated feature here. So you can see that the red line here is a variation from one year to the next, but it's speeding up. This could be perhaps due to some climate feature that's increasing the uptake or respiration of the natural biosphere. And we have this sort of slow moving variation superimposed on this blue line, which is sort of simply description of fossil fuel emissions. It's going up every year. And so once you add all these things together, you start to build up a very complex picture. So what you're seeing in the atmosphere is a result of a superposition, a combination of lots of different signals. And so one of the things that we have to do is to try to pull all those things apart. And that's why the models are really important. Because without the models, any model really, it's almost impossible to tease apart any of these individual signals that I've put here from the observed signal. Okay, so that's really the purpose of the model. Now, we're just going to carry on with the annual growth rates for a minute here, because there's some interesting points I wanted to make. There's lots of things you can do with the data without any fancy models, and models can be models. I'm being very general here. It could be sort of linear model. It could be a few lines of code just to describe what's going on. So this is a plot that is provided by James Barlow from a long time ago. But it's really useful. So for a number of reasons. So we've got growth rate here, CO2 growth rate on the y-axis, and we've got as a function of latitude. The lines here, we've got blue, red, and black. These correspond to different decadal periods. So in the 1980s, we have the red plot here. So the growth rate was reasonably small in the southern hemisphere, and then we start to see an increase in the northern hemisphere, as you would expect, because most of the fossil fuel activities are in the northern mid-latitudes. As we go to the 1990s, we saw a decrease in the growth rate. Okay, so the blue line for many of these latitude points are actually smaller, and this can be attributed to various things, including the collapse of the Soviet Union. And when we get to the 2000s, we see that the growth rate has significantly increased from one, so much further. So it goes from the red to the blue to the black, and you can see that at almost all latitudes, except for the highest northern latitudes, the growth rate has increased. Okay, so we're now approaching 2 ppm per year. Now, if we remove fossil fuel emissions, so we know that's the flux that we know the best. Okay, we know how much fuel is being burnt, more or less, from one place to the next. Now, if we remove that, the situation becomes a bit more, not a bit clearer. So we see that from the 1980s, this is the growth rate minus the fossil fuel emissions. So you'll notice in the y-axis we've got negative values here. We've got the same x-axis, which is latitude. Now with the red line, the growth rate, but this is the uptake. It's effectively the uptake of CO2 from the natural biosphere is about 1. So 1 ppm per year is being taken up by land and ocean. By the time we get to the 1990s, it's about 1.5. From the 2000s, it's almost 2 again. So 2 ppm is being absorbed pretty much invariant throughout the latitudes. And what's happening here is that over the past 50 years, the airborne fraction, the amount of CO2 that stays in the atmosphere, is approximately constant. So about 44% of the emitted CO2, so from fossil fuel and land use change, etc., stays in the atmosphere. Now, what that means is that natural biosphere, so the land and the oceans, are responding to an increasing atmospheric CO2. So every time the CO2 in the atmosphere increases, the natural biosphere is taken up more and more and more. Okay, so the result is that as a percentage, even though it's from an absolute value, it's much larger, the percentage of CO2 that stays in the atmosphere is approximately constant. Okay, so these are simple, we're looking at very simple, is a bit of data analysis, but there's there's some models here that we've kind of used. So, the atmospheric growth is a kind of a model that we're using to describe this data. Now, what does the in situ data? That's just one thing. The airborne fraction is fairly constant. Now, what other studies have done? So Charles Keeling looked at the amplitude. So let me just go back just to remind you. So, when we looked at this, at the amplitude of the seasonal cycle and the timing between the difference between where the seasonal cycle is on its way down and when it's on its way up. All these betray knowledge of what's going on in the terrestrial biosphere. So we come back to this, these studies here. These are quite high-profile studies. All of them, in fact, are in Science or Nature. So Charles Keeling showed that the amplitude of that seasonal cycle that we saw with the Keeling curve, that's increasing with time. And what that means is that that's effectively more biological activity. The amplitude has increased time, from 1970s to 1995. The amplitude at Barrow and Alert has increased with time. Now, more recent work by Heather Graven, this is 2013, she reanalyzed this. So she extended that time series to 2000s, and they also found the seasonal amplitude has increased at Barrow, which is in the northern hemisphere, and Mauna Loa. And so again, there's evidence that the biosphere is taking up more and more carbon, CO2, with time. Pretty much, that's consistent with the airborne fraction. And what she also found was that the phase of that seasonal cycle was decreasing. And she was arguing that the spring is actually getting earlier. So as the temperatures are warming, the photosynthesis is beginning earlier in the season, and actually taking up more carbon. So we are affecting the climate in some really profound ways, that we're affecting the ability of this terrestrial biosphere to take up more carbon. The extent to which this can continue is completely uncertain. We do not know whether this is going to continue for the next year, the next 10 years. There's got to be some limits associated with this, but we do not know where they are at this point. A more recent study, this was a paper that was published a few weeks ago. I think Prabir's on this actually, so he'll be able to tell you a bit more about this. So there was also evidence of the seasonal cycle over the Southern Ocean. So the ocean, there's evidence from the atmospheric data that the Southern Ocean is taking up more carbon than we had anticipated from inventories. So even with relatively simple data analysis and using simple models of linear increases, of there's a lot we can understand about greenhouse gases in the atmosphere and the fluxes that determine those variations. If we come back to this figure that we have here, just to sort of summarize what we've our current knowledge. So this is again the global carbon project figure, which shows the sources at the top, above zero, and then the sinks. Now what I've done here is add some uncertainties, because this is important, because all that we got the uncertainties. That's a measure of our ability, our understanding of that source. So land use change, as I said, it's very uncertain. The uncertainty is about half of what the magnitude is, right? So it's significant, although it represents about 9% of the total source. Fossil fuel, again, is about half a petagram of carbon uncertainty on a 9.5 petagram value. So fossil fuels are large. We have a relatively good understanding of these emissions. For the sinks, for the atmosphere, it's about 5.7, so about 47% of what's emitted into the atmosphere stays in the atmosphere. The uncertainty is relatively small, so 0.1. If we go to the ocean, we have a similar 2.7 plus or minus 0.5, and the land is 3 plus or minus 0.5. Okay, so there's a rough distribution of those emissions being absorbed by the ocean and the land. But the land estimate is generally residual. It's, once you've added up everything else, you get an estimate for the land. Now, these are the questions that we're left with, and I'm sure that many of your other lecturers have touched on this as well. So, which natural processes absorb half the CO2 emitted by human activities? Why does the amount of CO2 absorbed change from year to year? And will this change in the future as climate changes? These are open questions. These are questions that we do not understand, or we do not have a comprehensive, definitive answer right now. So how do we know what we know? Well, we know for a variety of things. So we have very detailed flux measurements of CO2, and I know some of you might be in the flux community. There's a big flux community for greenhouse gases. They take those data and they develop models, and so this is an example of a model which is influenced by this flux information, and you get maps. It's extrapolated to crazy. This is an example of a model. There's no way we have all this information, sort of continuous information around the world. This is why models are important. So you have some prior understanding of how a process works, you test it, confront it with some data, and that's how it's developed. And this is what you kind of it's the kind of information we have. We know where the fossil fuels are, because that's, we're responsible for burning them, of course. And now this was a database called karma.org, but of course we have lots of satellite data now that can pinpoint where most of these power plants are emitting. So we might not be able to see them necessarily with CO2, but we can look at co-emitted traces like NO2 and formaldehyde and CO are all traces that we can observe from space in very high accuracy and precision, and it kind of pinpoints cities and power plants across the world. What's been the workhorse for much of our understanding of the carbon cycle have been these measurement programs, these ground-based measurement programs, and this is an example of one from NOAA. And you can see, so there's a variety of sites here. So the red dots are the surface sites. We've got aircraft profiles and various things here. But what you'll notice is that many of the measurements that we have, the core measurements, are mainly in the northern some of these sort of don't work anymore, but most of these sites are in the northern mid latitudes, and so there are substantial gaps in the tropics. And as you can see, the tropics are supposedly a very large, have a very large biological activity. So GPP, gross primary reduction, is where the CO2 has been, basically where the CO2 has been absorbed. So the Amazon basin, the Congo basin, places in Southeast Asia are all places where we think we know that's where CO2 is being taken up. But you can see there's almost no measurements at all here. The situation is even worse for methane and nitrous oxide. So there's some gaps here. So this is where the models come in to try to relate what, those limited measurements to understand some of the fluxes. So this is where I've justified why we're looking at greenhouse gases. I'm going to define a model. Okay, so we've kind of, like I said, we've kind of already used some definitions of what, some models already to use the data to understand variations in atmospheric CO2. They were implicit in that analysis. This is my definition. Okay, so this is a model, it's a framework, typically mathematical, doesn't have to be, that tests scientific understanding through its ability to explain data. It should be sufficiently simple that it can, in principle, be rejected and refined with data. A predictive capability is developed through this refinement process. Now, this is really important. There's a number of points I want to raise here. Okay, so first of all, it needs to be able to explain data. If it's inconsistent with data, then it's not. The model is wrong. It doesn't matter who the famous scientist was that put the model together, or how fancy the model is. If it doesn't explain the data, it's wrong. It should be sufficiently simple that it can in principle be rejected. There's some very, very fancy advanced models that can effectively, you can change a whole range of parameters that would fit the data. But those kind of models cannot be rejected with data, because you can always fit data because there's too many parameters. So it has to be simple. We have to be able to understand it so that it can be rejected or refined with the data that we collect. Now, the last point, this predictive capability, that's really where we want to be. We need a fundamental understanding of some of the processes, but there is a predictive capability that we're really after. How will the carbon cycle or greenhouse gases change in the future? And without having that fundamental understanding that's developed through confrontation with data, it's difficult. You cannot have that predictive capability. And then sadly, we do have a whole range of models that is currently used by the community that do not have that predictive capability, although they would argue that they do. Okay, because they always you need to go back to this, what is called the scientific method. There's a short lecture by Richard Feynman that explains the scientific method. We must always go back to the scientific method. Okay, models are wrong if they don't explain data, period. Now, I'm going to talk about simple models, and these are very simple models at this point, but these kind of underpin some of the large scale models that we have. So this is what we call one box model. So these atmospheric box or reservoir, this could be over a city, or it could be over a continent. It could be over, could represent a whole range of different sizes. Now the X here, this is what we're after. This is CO2 or methane or any other greenhouse gases. And that X, that mass of X or whatever it is determined by a variety of different processes. I put a whole range in here. Some will be relevant to CO2, some will be relevant to methane, some will be relevant to nitrous oxide. So there'll be some inventory. So inventory, there's be an emission here that determines X, and there'll be some, so in the chemical production, for instance, and there'll be a loss, and there'll be deposition or a sink, another loss process. Now, what goes on in that box is really determined exclusively by emission, production, loss, and deposition, or another process that takes X out of the atmosphere. You also have to take into account transport. If this was a city, you would have an inflow of CO2 or methane into the city, and you would have an outflow of that from that city or continent. This box does not resolve spatial distributions. And for this purpose, we also assume that the box is well mixed. Now it's a very simple perspective, but it gives you an idea. It lends itself to describing some very simple concepts that we use all the time. So let's go back. So look, to the basics. Emissions. This is an important ingredient. So the flux inventories. So emissions and uptake. And so for CO2 or methane, we have fluxes from power plants and combustion. We have uptake, natural fluxes. We have deforestation and oceans. The point I want to get across here, so you might have heard this before, so trash in, trash out. If you've got a very bad inventory or it's poorly understood, then your model is never going to be, you're going to get a bad model. So if you have a bad inventory or poor uncertainty or poor inventory, then your ability to describe atmospheric greenhouse gases will also be poor. So this model is, so like I said, it lends itself to demonstrating some very simple concepts. So one thing is this concept of lifetime. So the lifetime, that should be tau, lifetime tau of X in the box is the average time that a molecule of X remains in the box, okay? And this is also important because you need to know how long this is going to stay around, but this will have implications for a variety, if this was an air pollutant, for instance, which I know is important in India, you have very bad air quality. The time at which an air pollutant stays in a box or a city will have implications for human health, visibility, all kinds of things. See, greenhouse gases are less so, but this is an important concept here. So you calculate tau with the mass of X, so m, divided by the loss terms. And the loss terms for this box is the flux out of the box. So we have the transport, the export of that pollutant greenhouse gas out of the box. We have the chemical loss, and we also have the deposition. Okay. So that's called the atmospheric lifetime. Is often called the residence time when the loss is a physical process. So if F out or deposition, these are physical processes. Okay, so that's why. So sometimes you might call it a residence time for a greenhouse gas or a lifetime. We might also be interested in the relative importance of each loss term. So we might look at the fraction of the fraction F removed by export out of the box is just the fraction of the importance of the export divided by all the loss terms. Similarly, we will sync specific lifetime. So for methane, for instance, we might want the lifetime of methane compared to or CO2 for export, the movement of that CO2 out of the box. Now the total lifetime is calculated in parallel. So you might have come across resistors in parallel. This is how you calculate the total lifetime. You have to do it this way because each one of the loss processes is happening simultaneously. So they're all taking a bit of CO2 or methane out of the atmosphere at any one time. So you have to add them up in using this reciprocal process. The other thing that we have, these are considered to be first order loss processes. So the more that you have, the more you lose. Okay. And we'll come back to, it's all a very dry theoretical thing, and I'm quite happy to share the slides. So you don't have to memorize all this information right now. But if we consider a first order chemical loss for X, whatever that is, that X is methane or CO2 with a rate constant, then the chemical loss is is a description of the chemical loss rate and the mass of that of X. So the lifetime is the mass divided by the loss. Now, if the loss is this first order loss constant, which is described by the rate constant, the rate at which a trace gas is lost in the atmosphere, multiplied by the mass of the gas itself. If you put that in the denominator, what you find is you have m divided by m times the reaction rate constant. So what you end up with is just 1 over the the rate constant. So we can generalize the chemical rate constant idea using this sort of simplification here. So we have the export of a gas, and we have the loss, and we have the deposition, then we can basically have, you can have a series of these rate constants which describe this, the rate at which a trace gas is removed from the atmosphere. And so once you've got that, you can simplify it. Now let's look at this in sort of less abstract terms. So this is the lifetime of atmospheric methane. So the lifetime of atmospheric methane is determined by a couple of things. So one is the hydroxyl radical. This is a primary oxidant in the troposphere. So this has a lifetime of about 9.6 years against OH. Soils, so soils that take up methane, this has a lifetime of about 160 years, and stratospheric sinks of about 120 years. Now these are acting in parallel, so think resistance in parallel. So even though the lifetimes of soils and stratospheric sinks are hundreds of years, very different to this decadal value for the hydroxyl radical, they do play a role. So once you add up the net, take into account these sort of long, sort of slow sinks, you find that it still plays a role in the net lifetime. So once you add up the net lifetime, you find that it's about 8.4 years. So it's about a year less because you've got soils and stratospheric sinks acting on the methane at the same time as the methane radical. Now it's much shorter than CO2, of course, because it results in larger interhemispheric gradients, and that's what you see in the atmosphere. So this is methane in the atmosphere. This is a famous curtain plot that's produced by NOAA. I couldn't find a more recent one, unfortunately. The colours denote the amount of methane in the atmosphere. We've got latitude and then year. So you can see there's a seasonal cycle. You can see it there, and you can see that's true for all the latitudes. You can see that there's a strong hemispheric gradient, so there's much higher methane in the northern hemisphere than there is in the southern hemisphere. Okay, so we're seeing this is a reflection of the sources that we see in the atmosphere, and this is affectionately known as the magic carpet. Now, the other thing I want to talk about is the concept of mass balance, and this is a really important point for a number of reasons. People don't necessarily understand this. So the mass balance is the change in the mass of X as a function of time is basically calculated as a function of the sources minus the sinks. So the sources in this case are the inflow, the emission, the chemical production, and the sinks are everything that takes X out of the box. So we have the outflow, the loss, and the deposition. So you end up with a sort of that's what is a very simple picture here. Now, the point of this. Let me just go back here. No, I'll go straight to this. Okay, so that's basically the atmospheric balance. Now, atmospheric methane is an excellent example of mass balance. So this is a time series of methane in the atmosphere from the mid 1980s to 2016. And what happened here was CO2 has increased throughout the 80s and 90s, and then it kind of plateaued for about 7 years. And then since 2007, is increased. In fact, it's actually accelerated since this last point here that I'm showing you this slide. And you can see that with the growth rate, it's the growth rate is kind of high, it's quite large, then it goes down to close to zero, and then it's come back up to values that we'd seen in the 1980s and 1990s. Now, the mass balance of the atmosphere, so this is increased, the mass of methane is increased. It's basically the gradient here through the 80s and 90s. The mass balance is zero pretty much here. That does not mean the sources are not active. It just means somehow the production balanced out the losses. Okay, so that is the situation here. So where the sources balance the sinks, we have the mass balance is zero. Okay, so the change in X with time is zero. But again, doesn't mean that sources and sinks are not acting. It just means they're balanced out. And that's what's happened with methane in the early 2000, 2007. And again, this is an open science question. Unfortunately, we do not have the data to make a definitive call on this. but we do not know why it slowed down in 2000 or why it resumed after 2007. So again, just give you a sense that many of the things that we take for granted, we have no idea why this happened, and we will never know why this happened simply because we do not have data. There's various hypotheses that go around that could explain it, but there is no definitive explanation for this. I'm going to, in the interest of time, I'm not going to talk about this. But you can see when I post these slides, you can take a look for yourself. But this is a work from Sunway out 2020. It's a very large-scale model study in which they pull together the state-of-the-art bottom-up and top-down emissions. And there's various points I make here, none of which are really important for what we're going to be talking about next. So in terms of, if we move back to the atmospheric models, I guess most of what you've been talking about in your lectures have been Eulerian models. So there's two types of models. There's Eulerian and there's Lagrangian. And I noticed that you have a computer practical working on Lagrangian. So I just want to make sure that you understood the difference in Eulerian and Lagrangian. So in this case, in both these cases, we have the mean wind flow from left to right. And we have various times. We have time in the past, we have time in the present, we have time in the future. Now, what happens here in Eulerian is basically the reference frame. So in this case, you would have a fixed reference frame. You would stay fixed, and you would have the air pass over you. So in this case, an analogy would be that the instruments are atop a fixed tower, and the air, the air passes through or pass around the instruments atop a fixed tower. So the blue lines here denote the air parcels. So the air parcels are growing with time because they're, we have diffusion and various processes in the atmosphere which will mix and change the size of the air parcel. So so you have this fixed perspective. Now Lagrangian, which you're going to be talking about, you're going to be using in the next computer practical, you are following the air parcel. Okay, so you are in the air parcel and you're looking specifically with what's going on in that air parcel with time. So that's a very different perspective to the Eulerian, in which you're fixed and the air parcel moves around you or through you. So in this case, with an aircraft, you'll be collecting data. If you're moving with the air parcel will change, and you're seeing the chemistry as the air parcel evolves with time. There are a variety of different models which describe either the Eulerian. I think I've got about enough time just to go through some key model types. So this is a simple one. It's called the puff model, and this describes the composition of one or more fluid elements moving with the flow. So in this case, the change. So this is a factory. We have the wind. We have the air parcel, which grows and dilutes with time. So it's a delta time. And so you're able to follow the evolution of the isolated pollution plume. It could be landfill methane. It could be CO2 from a power plant, for instance. And you're following this, and you can look at the mass balance of X. Could be any of these trace gases, in which you have the emission, the production, the loss, the deposition, and also the dilution rate constant. Okay, so of course the dilution is mixing with air parcels around, or the air around it. So the pollutant is getting smaller with time. It's a very simple model. A more complicated model is slightly called the column model. In this case, you would have, again, it's the Lagrangian model. We have an emission at the surface. The H is what could be the boundary layer height. So basically, the emissions are, we assume, a mixed boundary layer. The emissions are distributed in a column, and then we follow the column in time. So we can, the column can be split into a well-mixed layer, which can be with varying time. So in this case, again, you have a slightly different emission term, production term. So we have this emission divided by H, which is this mixed layer. And that could also reflect the fact that when you have a power plant, you have an injection height. These hot gases mixing very rapidly in the atmosphere, so you get emissions emitted from the surface, the source, and they get mixed very quickly throughout the boundary layer. And again, as you follow the the air mass, you've got this emission, we have this production, loss, and deposition, depending on which gas you're looking at. And this is a model that's frequently used in air pollution downwind of cities. It's a very simple model and easy to use. I'm just going to move on from this. This is basically we're starting to look at 3D models here. I'll leave this one for you to take a look at. But the point is, the rotation of the Earth is really important. Okay, so without rotation of the Earth, you have some fairly boring convective cells that go from the tropics to the poles. Once you take into account rotation, you have all kinds of cells, rotational cells, so circulation cells like the Hadley cell and then the Ferrel cell. So it becomes very complicated. But I'm just going to, I don't have time to talk about this today, but I will leave that up for I'll leave that for the notes so you could take a look at that. But I wanted just to finish off, because I'm conscious of time, that I wanted to look at the modelling of atmospheric greenhouse gases in 4D. And this is now an Eulerian and Lagrangian perspective we're talking about here. So those other models we talked about, the puff model and the collar model, they're relatively simple. You're basically following a very simple trajectory. When you start looking at 4D, when you've got complicated winds, you've got 3D winds, and you've got as a function of time, the equations you have to solve become much more complicated, much more elegant, but they're much more complicated. So you have the change in the concentration of a greenhouse gas, for instance. You have to solve the material derivative. So this takes into, you're looking at the wind vectors and the change of that trace gas, greenhouse gas, as a function of the vector wind. And then you've also got the production and the loss. And now you're looking at sort of 3D space. So you're looking at X and Y, the production and loss could be 2D at the surface, but there's also 3D production and loss in the atmosphere as well. So these equations, this is the kind of equation you'd be solving for an Eulerian form. The Lagrangian form is much simpler because you're following the air parcel. So you don't have to worry about this first term because you're following it, and so you only have to take into account the production and loss. The Eulerian models, this is an example. So basically, when you're looking at these sort of global 3D models, we divide the world up into grid squares or grid boxes, and you can see here there's typically about 10 to the 7 grid boxes. It gets quite computationally expensive very quickly. And so in this case, for these grid boxes, so you've got as a function of height and all the the X and Y, be latitude and longitude, you're solving those continuity equations for individual grid boxes. So for 10 to the 7 grid boxes, you've got to solve the continuity boxes. And just to give you a sense of the kind of resolutions that we're working with right now, looking at greenhouse gases, and it's about 25 kilometers on the global scale, so 0.25 degrees, and a vertical resolution of hundreds of meters. So these are the kind of, so we now move, when we start look at these equations, we're solving that for every single grid box. So now it becomes more of a computational problem, and it becomes very difficult to do this without having some clear idea of how to do the calculations. Right. Okay. So I am running out of time. I've got 4 minutes left.
So can you please finish in a few minutes?
Yeah. I'm going to finish up right now. Okay. So I'm just going to finish up now. So the end point is something like this. So when we look at solving these continuity equations, we have everything pulled in. This is an example of column CO2 for from the GeosChem model. And what you see here as a function of time is that we're starting to see, this is August, we're seeing uptake in the southern hemisphere, we're seeing emissions in certain places. We changed this now November and December, we're starting to see the northern hemisphere emit CO2 at various sources. So with these very simple concepts, we get to pull together, we can actually pull together a very complicated, realistic picture that we can confront with data. So I will finish there. I'm very happy. It would be much more fun to do this in person, and we'd have much better discussions. But I'm very happy to share the slides that I've just given you, because we've had to go through them very rapidly. And if you have any questions, I'm very happy to answer them. Okay, thanks.
Thank you, Paul. for giving a very, very nice presentation, starting from very basics to observations and then modeling. I think this is a very good lecture, especially for the students. And I think there are some questions which probably you may answer. The first question, it is posted by Praveer. He says, nice, Paul, that you raised the issue of political willingness to reduce CO2 emissions and our science solid enough already. COP26 happened next door to your university. What is your opinion on global methane pledge versus much needed stronger commitment on CO2 emission reduction?
So the global methane pledge is a step in the right direction. So this is a 30% reduction by 2030. It is not. It's not going to be super effective. I mean, addressing methane is important because it's a quick. It's a rapid. It could lead to a very rapid change in quickly because the lifetime is about 10 years. So by reducing that has a very rapid, it can have a rapid impact. However, it will not address the 1.5 degree target. You really have to have a very clear and rapid plan to decrease CO2 emissions. So in some ways, it's very welcome. In other, but we have to really focus on CO2. That's the big one. And that's the one that's going to help us reach that 1.5–2 degree target. By ignoring that, we are just going to be way over. Is that answering the question?
Yes, thank you. Well, exactly that is my point too. And yes, I think somehow because of the global methane pledge and the CO2 was somewhat. I mean, they could escape. The political parties, political systems could escape the CO2 discussion. And I was hoping that it will happen more on CO2 this time. Yeah. Because IPCC AR6 were pushing much more on CO2 this time and clear idea about that nothing but CO2 can help us in the long term.
I agree. Absolutely. Yeah. I don't want it to say. I didn't want to say it was a distraction, but it is. It's important, but it's really just it's got to be done with a very strong reduction in CO2. So I agree with you. Yeah.
Thank you.
Next question is a very basic question and posted by one of the youngest participants, Vaishnavi Pandey. She asked, according to IPCC, abundance of carbon monoxide in northern hemisphere is twice that in southern hemisphere. What is the reason behind this?
Carbon monoxide. Oh yeah, okay. So carbon monoxide's okay. I'm just trying to read the. So there's two reasons. So carbon monoxide, CO, is a production of fossil fuel. Well, it's a combustion basically, and also the oxidation of methane and other VOCs. So when you look at in the northern hemisphere, most of that's going to be due to combustion. And we're talking about large scale, fossil fuels, but also during the summer, you're seeing large parts of Canada and Western North America and Siberia on fire. That also produces huge amounts of CO. In the southern hemisphere, we do have large sources of, there's fires in the Amazon basin, in Southern Africa and Australia, but these are relatively small. Even so, to some extent, you can approximate the CO in the southern hemisphere by methane oxidation. As that methane oxidation in the southern hemisphere represents a larger proportion of CO than in the northern hemisphere. So that's the reason behind that. Did you mean carbon monoxide or carbon dioxide? I wasn't sure, but that's the reason for carbon monoxide.
So there is another question by Praveer. No CO so far in this talk. Please ask relevant question. Oh, there is a comment.
That's not a question.
Comment. Yes. Yeah. Okay. So next question is by Pramit. Are the DVGMs used to compute the terrestrial carbon sink properly calibrated for all the biome types in different climatic zones? Some zones like India are heavily less studied in this regard. Can this contribute to, at least to some extent, to this problem of sink estimation?
Well, I mean, so all these models are wrong, right? All our models are wrong for some reason or another. The DGV, but the dynamic vegetation models, they are influenced. I mean, the way they've been developed and calibrated against data. And you're right, as with other kinds of models, they're calibrated with data where they're collected, and most of the data is not collected in places like India. So you're right that, you know, if they could improve, you know, if the Indian science community wanted to improve these models, they could, and they could probably play a really key role in improving these models, because I suspect there's lots of countries around the world that are poorly, you know, just not taken into account, if that makes sense. So I think that, I mean, I don't know. I mean, Prabir might be able to say something, but I don't know the Indian carbon balance. I mean, there isn't enough data over this country to make a call on it. I mean, it's a really complicated country. You have it's wonderful in terms of the diversity of sources and, you know, emissions of methane and CO2, but at the same time, it's, you know, there aren't enough measurements, I think. So I agree with you. Yeah, it could improve the models if you had more measurements from India.
So next is the appreciation by Vinu that about your definition of model. So I think this is appreciated by entire audience. Next question is by Chaitanya. Can we get your presentation copy? Oh, okay. If you are okay,
I can send it to you, and if you can circulate it, that would be great.
Oh, thank you so much. Vinu asks, curious to notice that there is no clear explanation why methane zero growth rate in 2000-2007. Yeah,
I know. So there's a number of science questions. You know, we tend to think that, you know, we know about CO2 and methane, and we talk, it's in the news all the time, but there are so many, you know, basic things we don't know about these two gases in the atmosphere. And one of them happens to be, we have no clear explanation why there was zero growth rate. There are, like I said, there are hypotheses, but there is no definitive explanation.
So Paul, do you think that in future, if we have this kind of situation, that is plateauing of methane, we'll be able to answer that? Do you have enough observation?
Yeah, well, it's much better than, I mean, unfortunately, I mean, what's going to happen? I mean, I have no time. I could have given a couple of lectures here today, but I think one of the key aspects, one of the key data sources that is now really important are subtle observations. And I think that Harj gave you a seminar or lecture a few days ago. These now are incredibly important. So places, you know, so my group has identified, I mean, Prabir's done something similar as well, but we've looked at new sources of methane that we had no idea existed in Eastern Africa, for instance, wetland sources. So, you know, we should be in a much, much better situation now. If there's a new source or something's really odd going on in the atmospheric methane, we have a much better way of picking that up and understanding it with the subtle observations. And these subtle observations are going to continue. We have like a continuous time series from 2010 onwards, and there are plans to launch satellites for the next, you know, 5-10 years. So it's going to be much better.
Right. So there is another question by Chaitanya. If the natural uptake is responding to the increase in CO2 over all the latitudes, annual growth rate slide, what is causing the steady increase of CO2 growth rate? It should have stayed constant at least. Any possible?
No, that's a fair point. So as a percentage, it's the same, okay, but, you know, these things are, you know, so the airborne fraction is at 44%, but of course you know, every year the fossil fuel emissions are going up, and the uptake is increasing, so you're starting to see, you're just basically seeing an increase in CO2 it's relative. It's pretty much it's like 2 ppm per year. But the more CO2 in the atmosphere, the more that the more uptake. It's sort of compensating. So there is a steady increase in CO2 growth rate. That is basically because only a certain percentage is being absorbed by the land and the ocean. The rest is remaining in the atmosphere. So you're just getting an accumulation of CO2 in the atmosphere.
So next question is by Santanu Halder. May you kindly describe why is the phase of CO2 decreasing?
I think that's referring to an earlier slide, and that was so here we are, the phase. Yeah, so the phase is decreasing. I think it's basically because the spring is getting earlier, so we're starting to see an earlier spring, and we might be getting a sort of later autumn in some places as well. So it's warming. So there's vegetation is, even at high latitudes, there is a longer growing season, and the growing season when it's warm is becoming earlier every year. It's just a consequence of climate.
Then next question is by Mihir. Dr. Paul, would you mind sharing your presentation? He has already agreed.
Yeah, that's fine. Yeah, that's fine.
So Pramit says, just curious why it is called the magic carpet.
Oh, I think it's just an affectionate name for it. I can't remember what it is now, but it's because it looks like a magic carpet. It looks like a carpet, like a Aladdin. I don't know. It just looks like a carpet. I think it's just that's what it. There's no real reason for it.
So probably there is no more question.
Sure, that's fine. It's been a pleasure talking to you. And again, I last time I did this in person. It was much more fun. I hope that the next time you do this, we are able to do this in person.
Yes, that will be great for all of us.
Yes, but I will send you this. I will send you the slides. There's lots of other slides in here, so you can. People will be able to look at this sort of in more depth, because I've had to run through them very quickly. So you're very welcome to have all of them. It's fine.
Yeah, thank you so much.
Sure.
Fantastic. So, yeah. Can I share one slide, just a little bit?
Oh, you want to go back to a slide?
Here? Yes. When Paul is here, I want to show one thing.
Yes, please go ahead.
I think. Can I see it? Can I see it?
Yes, please.
I think I don't see my screen somehow. I want to show Paul's picture from last meeting because he mentioned that there is so much fun last time.
Oh, from this Kolkata.
Yeah, GHG-2. He was.
GHG-2, yes.
Yeah. Prabir keeps everybody's photographs. Be careful.
Oh, what happened to that? Yes, this one. You see that? Paul bought an ambassador already.
Kolkata based.
On the bottom left.
Oh yeah. Yeah.
He bought an ambassador.
Yeah,
Hindustan Corporation, right? Hindustan Corporation car. Yeah, I just wanted to show you that.
Hindustan Motors.
Hindustan Motors, yeah.
Yeah, it's out of phase. It's
yes.
Stop production now.
But Paul could get hold of one before it out.
Yeah, since you're talking about last time's meeting GHG-2 that I could not attend, but I met Professor Palmer in that summer school in 2016, the Gauge UK summer school.
That was good. It was fun.
Yep.
Yeah, that was also fun.
I'm glad you're continuing with this. It's a nice.
Thank you very much.
Yeah. That was in NOC Southampton.
Sorry, say again.
That was in National Oceanography Center, Southampton.
Oh yeah. That's right. Yeah. Oh, yeah, I forgot about that. Good. All right. Okay. So, Vinny, do you want me to? So I send you the slides, or should I send?
Yeah, please share the slides with us. We'll put up in our website. I mean, workshop website for some days, so people can download it. That would be great.
Yes.
Yeah. Cool. So have you got a computer practical now? Have you?
Actually, today is a slight change. One more talk is there to accommodate by Yogesh, because we had a technical problem 2 days ago. We could not accommodate his talk. So would the panel members kind enough to accommodate it now and then move on to the panel discussion?
Yep. But I think it was like a kind of, I mean, just to conclude, I mean, this kind of thing, like it's like amazing, like 4 days, we only had one technical problem, one lecture. That's it. I mean, but everything went so smoothly.
That too for the first time in our institute, it never happened.
Everything went so smoothly, like for 4 days. Yeah. Fantastic. Yeah. So it's like incredible.
Yeah, that's impressive.
Yep.
Okay, shall I sign off now then, so Yogesh can start?
You could, yes. Thank you very much.
Okay,
bye,
thank you, Paul.
Yeah,
thank you very much.
See you all.
Yeah.
Take care.
Very
Bye.
nice lecture. Yes.
Have a nice holidays.
Bye.
So we can go for the next talk.
Yeah.
Yeah, let me make this announcement. So there are going to be some difference in today's schedule. As I mentioned in the morning, that today's hands-on, the people who are preparing it are under a lockdown situation in their institute. They may not be, some of them are affected also with COVID. So we may not able to accommodate that now, and we'll announce the next plan as soon as long as this talk is going on, and then we will inform the participants. So now Yogesh may give his presentation. By the time we'll make a decision about the next plan. Thank you.
Can you see my slide?
Yes.
Yeah, we can see your slide. Can you click the hide button? That
hide button. Yes.
Yeah, I will go fast so that it will. So I will not take much time, so that panel discussion should continue. Okay, so good afternoon to all, and then this is basically for those young researchers who really joined here just to learn about greenhouse gases research in India, or about basics. So there are some basics in it, and there are some results. So the topic is different techniques and platforms used for GHG monitoring in India. Basically, this is I am showing only IATM program, because Chaitanya has covered almost all the GHG monitoring activities in India, and also those are missing and Chaitanya has not shown. I am covering here. Okay, so just for young researchers, this is greenhouse effect. Basically, they must have heard about this greenhouse effect. So this is kind of you can imagine some glass house kept somewhere in agriculture field. So glass allows the incoming solar radiation, but doesn't allow to the radiation which is going back. So same thing happened with the atmosphere when there are greenhouse gases. So solar radiation, basically it comes, and when long wave radiation goes, these are trapped by the major greenhouse gases like CO2, CH4, N2, and water vapor also, and then they re-radiate back. So it changes the entire energy balance of the atmosphere, and then so many things happen like climate change and global warming. So many big words you must have heard. So this is very basic of greenhouse effect. And basically there are three things why we should this is basically got more attention. One is radiative forcing. Right side you can see the radiative forcing of different greenhouse gases. For example, carbon dioxide has close to 1.8, and then methane, and then halogens, and then nitrous oxide, other gases, and they are cooling also due to aerosols. And second one is a global warming potential of gases, and then lifetime, of course. So basically global warming potential, I'll tell you, those students who do not know, it's a kind of a measure of energy by 1 ton of carbon dioxide emitted in the atmosphere. So it is like and the global warming potential of CO2 is 1. It's kind of it's a reference. So in comparison of CO2, what is the global warming potential of other gases we measure? So generally for the methane, and then it is taken on 100-year time scale. So for the methane, if we take 100-year time scale, so global warming potential is something like 20 or 30. But if we take methane lifetime scale, like 12 years, so global warming potential is 80 times more than CO2. So, and then since its lifetime is less, so we much focused should be given to methane also. Now it is going on. And then lifetime means once CO2 emitted, and then the part is absorbed by the ocean and then by the biosphere. Ocean sink is very long time period, and then after that whatever remains in the atmosphere, that is a net that stays in that atmosphere for the hundreds of years in the time scale. So that's why we need much attention to these gases. And then the major source is basically fossil fuel. You can see this picture from Global Carbon Project, that annual fossil fuel CO2 emission by continent. So you can see this Asian picture. This covers entire Asia. You can see India, China, and these places, and then other places like North America, Europe. They are slowly stabilizing and these things. So this is the major chunk of greenhouse gases source. And this is the installed capacity of coal power plants worldwide as of the 2020 by select countries. Like China has the biggest. So still, I'm not sure, because I have taken from this website. United States also have some coal power plant. They are purely based on. So India is third. So if we see Indian perspective about this coal, which is basically major fossil fuel, what is the position of using coal in India? So this is 31st March 2005 power generation sources, and then 31st March 2019. And this data is released by the government. It's a CO2 baseline database for the Indian power sector from the Ministry of Power, Government of India. You can see in 2005, the coal for generating a power was used just 55%. But in 2019, means another 15 years, it became 70. Means this ratio is increasing. And what is decreased basically? Decrease is hydro. Hydro was 26%, and now it became a 16%. So almost 10% decrease, and which is basically because we need power to feed people, for our industry, and then for the household and these things. So we need to sustain it. So coal is basically increasing for the power industry. So, and what about the CO2 emission due to fossil fuel over South Asia? So this is basically CDIAC data, and then from Patra et al. 2013 also it was there. So you can see this is over South Asia, all the countries. This is fossil fuel CO2 emission. Bhutan, Bangladesh, India, Nepal, Pakistan, Sri Lanka, and black line is total. So all other countries except India, all other countries lies here. Of course, they are smaller and they do not have, in comparison of India emission, but Indian emissions are here, just almost parallel to the total. And this is due to of the large country, large population, and then increasing economy. So we need more energy. So fossil fuel emission is here. So just to understand these emissions, the only thing is we need observations and model. So models are really discussed last 3 days, and observations also discussed. So I am giving some more flavor to the observation. I am the last batsman of this workshop. So I am giving just you flavor of what IITM is basically doing. GHG monitoring at surface sites. GHG monitoring we have done on ship deck, and GHG monitoring on board airplanes, and then also forest ecosystem. Forest ecosystem also, some of the plots were shown. I will show something. So this one is, you must have heard in many talks about Senegal. So this is IITM Observatory 2019, and so, sorry, 2009 we have installed. And the observatory is within the campus of BSNL tower. And this is the IITM tower, and then here is the container. And outside this campus, it looks like this. It's not completely forest, but it's a quite good grass. But during the dry season, it is completely dried. So here is the tower, and then you can see the mountains. It's a big, huge mountainous area, and then here is a basically lake. You can see it's a big lake which feeds water to the Pune. So the methodology we have started in 2009 because that time there was no Picaro, and then that time we have installed a gas chromatograph laboratory at IITM with the help of Max Planck biogeochemistry. So we have bought the sampler from LSE France, and then the flask from the Max Planck from some company in Germany, and 2 flasks sampled at a time, 1 liter flask, and then we bring it to the laboratory, and then we analyze it, and then calibrate with the NOAA standards, and then we send the flask to the flask conditioning unit. So this flask conditioning unit is basically the entire design, everything, the idea was taken from the Max Planck. I will tell you why it is actually. And this is a closer plot of the tower, and then the med sensor. This was basically the inlet, and then inlet was coming in the room, and then this 1 liter flask we used. So I was talking about the flask evacuation and conditioning system. So we have developed it here, but the idea was taken here. So when we sample the flask, because this is rounded flask, so what happened when air comes inside, and it really moves inside the flask. So and then there are chances of sticking various kind of molecules like gaseous molecules or many other thing on the wall of the flask. So before sending to the field, what we do, we basically evacuate it here, just create a vacuum inside, and same time we heat it with the air blower from the top. So air comes, it gets heated, and then at the same time it evacuates. So there is a fixed time, almost 72 hours. This process is done at 60 degrees centigrade, and then we close the flask, okay, and keep it, store it, and then once we send it, then we fit the flask in the sampler, then we open it, so that the air outside which is coming in the flask is the same air which we are going to sample. So first the flask is flushed for 10 minutes, and then it is filled. So this was the entire procedure. So this is the back trajectory of Sinhagad. This is from Dr. C.G. Kumar's group, and this is potential emission sensitivity. You can see during winter time and then during post-monsoon time, the area which is basically covered, the sensitive to this site is almost the land part. And pre-monsoon and then monsoon time, it is basically the oceanic as well as coastal part. So this is the data, the long-term data. Basically, it starts end of 2009, and we have showed here to 2019. Our observation were hit during the COVID lockdown, because everything was closed and we could not sample the flask and these things. So there are some data gap, but that we are just analyzing how to fill it. And also we will do some, we are going to put a Picaro over this site. So this is the methane over the site, same, starts 2010 until 2019. And now the GHG monitoring site in Asia, if we see, so there's 3 more sites, Hanle, Pondicherry and Port Blair. This was basically from the CMAX Bangalore, that time now 4PI, in collaboration with the French guys. And along with that, SNG and CRI also was there. CRI was stopped in 2012. So these are their sites. Basically, you can see we are talking about the Hanle sites operated by LSE France and CMAX Bangalore. So this is Hanle site. You can see the trajectory. It never looks India. So even during the summertime and April, May, June, and then October, November, December, and then this time, see, it always looks in one direction. And other 2 sites like Pondicherry and Port Blair, it is basically coastal and oceanic site. So this is their data. This is published in LIN 2015, and basically this is Hanle versus Pondicherry comparison. Data starts sometime in 2007, and it goes to 2012. This is, I'm showing published data because I do not have data, just I have taken figure from the paper. And this is Halle between the global site KZM, and this is Walling 1. So KZM is basically here, this site, and Walling 1 is here, and then Halle is here. So these three sites are compared along with Port Blair and Pondicherry. So you can see Halle is a global site, more smoother, and then Pondicherry has that time in 2008, 2009, they had a outliers values even till 400 ppm. And Port Blair site, since it is coastal site, so it was also sampling very, I think, based on the transport, it was sampling mostly the oceanic part. And this is the atmospheric methane from Halle and Pondicherry, Halle, Port Blair, and then these two other sites. So you can see that Pondicherry is a coastal site, so has a larger amplitude in case of methane than the Halle, and Port Blair also has a larger amplitude. We have done GHG observation at ship deck. This is long back. We have taken sample that time. We did not have any in situ observation in hand. So the aircraft, the ship route was started from Chennai, and then this was the basically its route, and then it is basically moved and then came back here. So the sampling was done at these those designated, basically this is July 16, 17, 18, 19. So every day it was done, August 12. And then we have tried to basically see the land ocean contrast using this data. So what we have done, we have just compared with the columnar CO2 and then with the observed data, and then we have seen some peaks. For example, we use the TM3 model. During those particular times, probably it was meteorology and it was a model, and then carbon tracker 2 models were showing, and then observation, and then airs also showed such kind of peak. So those peak were seen in different years at that particular time. So it was like basically the land ocean contrast in the observation of CO2 or Bay of Bengal. It was that time, in that year it was observed. So this is basically fossil fuel and biosphere tracers, how the peak seen here, basically which contributed terrestrial biospheric fluxes and fossil fuel fluxes. I will not go in detail. This one is basically the MetFlux project, which is basically run by the IITM. Dr. Supriya Chakrabarti is PI of this project. Pramit and various other people are involved. So we have a tower at different locations in India. So this is overall tower. So Kaziranga National Park, this one is operational, and then we had a tower in Darjeeling, and then the Sundarban Betul, this is Narasi towers. And Srinagar, Mehboob Nagar, we had basically Srinagar is our site, and then Mehboob Nagar they had a short period of time. So basically the MetFlux tower, which is in operation, is basically the Kaziranga National Park, currently in operation. So this is the Assam tower. It's a 50-meter tower, as we had discussed first day, and then you can see this is above the canopy height, and there are instrument at 30 meter, and basically the CO2 flux, which is measured here as well as other places. For example, this Betul and Mehboob Nagar, and then other like Kaziranga National Park and these things. So these are compared here with the 2-3 sites, and so Betul result basically from Narasi, from some published paper. And this is basically carbon sink is compared at different sites from Betul and Barkacha, means it's over Ganga basin during different months, and then Mehboob Nagar and Kaziranga National Park, Sundarbans and Pichavaram. So this one is basically compared long back, I mean during the initial observation period. This is from Pramit's paper. So this is basically ecosystem atmosphere CO2 exchange. So any GPP and TER between 2016, 2017, and 2018. So during 1 year, 2nd year, and 3rd year. So how basically any total net, how it varies during different years and how. And this is basically Koshi Katarmal site during 14 and 15. All the three were compared. Now we have done some airplane measurements over different cases. So this is picture of July 2018. We use basically B200 aircraft, and then this is 14-15. This was over Ganga Basin, and that time we did calibration before and after the landing of the flight. We did not have permission to fly the cylinders in the aircraft because the high pressure cylinders. So we have calibrated in that way, and we use basically the Picaro. The instrument 2401M, especially designed for the aircraft monitoring. So we did vertical and horizontal observation till almost 8 kilometers. So 2014, our target was basically Ganga Basin. You can see this yellow area. It was sampled over here. And 2015, 18, and even 19 also there was there. So we have used basically the Maharashtra, Kolhapur, and then Solapur area. So this is the initial result from this. This is basically under preparation. Very soon we are going to publish along with other data. So this is methane vertical profile over Kolhapur, and this is carbon monoxide over Kolhapur. So you can see some peculiar trends. I mean, with the height it increases, and then there is some threshold. After that it decreases, and carbon monoxide also shows a similar kind of pattern over Kolhapur. So the black is basically mean line of all the flights, and then gray is various flights. And this one is basically between 0 to 2, 2 to 5, and 5 to 8 kilometers between CO2 and methane, how they are correlated between each other. So if we see the same thing, methane over Varanasi. So Varanasi during it was September 14, and Kolhapur it was July 15. So it was in the monsoon range, but Varanasi at the surface it was high, and slowly when we go up it becomes constant. So this was basically the background value, but it shows obvious at the surface high and then upper height at low. Carbon monoxide was showing similar. And when we compared with the model, we used ACTM from Dr. Prabir, and then LMDZ from LMDZ group, Michel Ramanet. So we found a similar structure. You can see almost overall it captures even the magnitude also, similar kind of structure is seen. So basically it is a meteorology which is captured, and then Ganga Basin also, it is both are captured. And we did over Mahabaleshwar area. So that also it looks model. Basically model structure, if you see without observation you may not understand. So unless we have observation you may understand. So this is just model initial validation. So basically okay, I will not go in detail. This is purely chemistry. So we have seen the vertical, basically back trajectories. This is 2 kilometer and 5 kilometer. So probably at 5 kilometer, what we are getting till King due to this one, because there is a transport from more polluted areas, and then it is getting here. This is just based, trajectory based. I'll not go in detail. Okay, so this one is Tall Tower GHG monitoring in central India. This is almost hit due to COVID lockdown, almost 2 years. It is hit. Our plan was to initiate in 2020 March, and when we wanted to move the tower, immediately lockdown happened. So now everything is finalized. The next week tower is going to start for installation, and by January end our Picaro will be up over there. So basically this is the This is called atmospheric research testbed at Silkheda village, and 72-meter tower. Basically, if we take up GHG, so it will be tallest tower for GHG. And this will be fully automatic observatory, real-time data transfer facility, and real-time storage and display at IITM. We are going to display the live data here, and the data also will be copied and analyzed. So this is the, you can see the schematic of the tower, and this is the location. So during the dry time, you can see the date, 23rd February. So this is the site basically, and then it's completely dry that time. It's a completely flat land. And these are the heights we have planned there. They will have AWS at automatic weather station at 6 levels, and GHG at 3 levels. And we'll have eddy coherence at 2 levels over here, and then a lot of soil instruments. So you can see the instruments which is going to install there: CO2, CH4, COS2O, and then delta 13 C of carbon dioxide and methane at 3 levels. So we'll have a 2 picaro, one for basically CO2, CH4, COS2O, and then 1 picaro for isotope. And we'll have eddy coherence, and then we'll have a soil CO2 flux system, then soil heat flux plate, multi-component weather setter C6, and then we'll have infrared thermometer, then power sensor, and then net radiometer, and then so many soil sensors, electrical conductivity, soil temperature, and these things. So this is the basically the transport picture, back trajectory of Bhopal site. You can see almost winter, pre-monsoon, and post-monsoon. It really samples the continental part. Even monsoon also, in a major part is from the India. So looking the site potential of the site, it will be really very good site. Around the year, we are getting the data which has basically which is looking the Indian continent. So apart from this, we have given input to the policy makers also, as some figures you must have seen in the Shamil's talk. Basically, this is called a BUR, means biennial update reports, which is submitted to NFCCC by the Ministry of Environmental Forest. So BUR 1, 2, it is compared with another study, and this is the EDGAR data. Basically, this is the methane emissions in teragram per year. And then you can see the EDGAR data is here, and then the estimations of this paper were here, close to this BUR and BUR2. So it really shows some confidence in the reports, which is basically submitted to the NFCCC. And this paper was basically Anita Ganeshan published 2017, and then the same thing it was there. So you can see this is the line which was the 12-month running mean and estimated line, and there's a black line from the Indian government. So basically it was closer, and then this orange line is basically from the EDGAR. So EDGAR was overestimating in these two studies, and then this is just published in biennial update report. And then I wanted to give some flavor. Mehul showed some data about COVID-19 lockdown, what happened to air pollution. So I'm touching just CO2 emission reductions, what happened. So there were some initial publications like temporary reduction in daily global CO2 emission during COVID-19 forced confinement. So this paper even published in 19 May itself, because lockdown started March, and then it just 2-3 months it came. So this was the basically situation. So change in global daily fossil fuel CO2 emission by sector. So you can see the surface transport and then aviation sectors all were hit basically. From January to March till April, how it came down, all industry and surface transport, public, residential, aviation. So basically residential was same because it was not because it was basically related to public, but everything was hit. And if we see the country wise, so how it came down, like China, US, Europe, India, and then so rest of them. So entire all the emissions came down from 2020 January to May. This is particularly from some another paper, but looking India. So India sees CO2 emissions reduction by 15.4% till June 2022. So this was published in some Liu et al. 2020. You can see after the Holi, immediately when lockdown came, so the emissions basically came down. Indian, and then this is a global, and then this is another countries. So this is from one more study from Carbon Monitor. So till October, it really compensated, and then still it was 9.87%. So I checked from the government data, basically the power generation using coal. So just I took the data from Power System Operation Corporation, Government of India. They publish their reports and they give that what is the power generation using coal in mega units. So basically in 2020 it was hit. So this is 2019 same time, but 2020 basically you can see it came down. I mean, the coal was less used because we did not need the power. A lot of industry were shut and these things. So power generation sources using coal was really reduced. So this was basically lockdown effect. And but the question is, this is for the young people. I wanted to just show you something. However, there was no reduction in the observed atmospheric CO2 concentration, though emissions were reduced. Why it is, I'll tell you just using some small photograph. Just I'll give you message. So you can see the Mauna Loa CO2 concentration observations. So it was same even April 2020. I mean, you can see it is touching 418, 415, and then again it was same till October 2020. Usual seasonality, there was no change. Why it is, I'll tell you just for the young guys. This is atmospheric CO2 concentration seasonality at Pune during 18 to 20. So we had methane and then atmospheric CO2. Just we took like January to just 1 year, one seasonality. We have seen there was no change. Almost it was same. So whether the global drop in emissions will have a noticeable impact on atmospheric CO2 concentration. So what is CO2 emission, CO2 concentration? First, let us understand to all those guys. So this is the climate myth actually. So CO2 emission do not correlate with CO2 concentration. It is easily demonstrated that there is no correlation between CO2 emission and atmospheric CO2 concentration. Over the 3 years from 79 to 82, I'm giving example, when CO2 emissions were decreasing due to the rapid increase in the price of oil that drastically reduced consumption, there was no change in the rate of increase in atmospheric CO2 concentration. Why? So this is one schematic I prepared. I took a picture from Google. Just you understand, this tap is basically surface CO2 emission, right? And this entire bowl is our atmosphere. Okay. So what we have done during lockdown, we have just reduced this tap. Once you reduce this tap, what will happen here? This will be as it is. So atmospheric CO2 concentration will only affect when you are going to close this tap for a longer time and you are going to reduce the emission for a longer time. It means if this tap is not fully closed, it has a leak, then nothing will happen here for longer time. So this was the reason there was no effect. So this is for the young guys why basically atmospheric CO2 concentration did not have any effect. So this was it. Thank you. Can you hear?
Yeah, thank you, Yogesh.
Yeah.
So Priyo, can you take through the questions?
Yes.
I am just let me first, should I unshare my PPT, then we can talk.
Maybe you can keep the PPT because if some doubt.
Okay. Right. Yeah. Okay. Go through.
Yeah.
Questions.
Just wait. I'll see.
If no questions, then
No questions are there.
There are
questions are there. I think this is from Chaitanya. He posted a question. Not many flux measurements from Western Ghats region except Srinagar. Any specific reason?
Yeah, well, Chaitanya, Western Ghats basically we have on site, but only due to logistics we could not do that. But the Western Ghats and the Srinagar, almost we have seen the height also is same. The mean sea level height is same, and also the site where we have that has a more disturbed site because nearby road is passing and then we have households over there. So basically that site is not very suitable for the GHG observation. That's why we did not think about this.
So another question posted by him. What changes are made in Picaro for aircraft measurements? Any corrections were made in the data during post-processing to account the sample flow rate at different altitudes?
Okay. So basically, what we have done when we have calibrated the instrument just before flying and then after the flying, because after the flying is very much important because that time instrument entire optical system is faced some variability and then it is the air everything is the same. So we have tried to, so we could not fly it in cylinders inside the aircraft. So that time we have found that the instrument was very stable. Even during the flight also we have changed the cavity pressure. Basically the cavity pressure, if suppose it is changing with the altitude, then in that case the monitoring will affect and then we need a more correction or we need a more basically data filtering. But we have found everything was all right during basically flying, and then we have monitored the Picaro continuously, and then even till 8 kilometers we have measured vertical profile. And even what we have done, we entered in the Arabian Sea almost 200 kilometers inside, though it is not much inside. We have done vertical profiling over there also. So nothing, I have not seen any unusual thing. So I rely this data very much, and you have seen in one paper where Rajesh used this data for comparing his inversion result. So that was really very reliable data and then used for the model validation.
So there is a request by Mihit Prajapati. He's wondering if the participants can get the presentations made by Vinu and Yogesh.
We will give you. Yeah, you need a file, right?
So Chaitanya posed a lot of questions. The third question by him is how the sampling will be done at our tower for Picaro analysis.
Yeah, you mean are you talking about the sampling in upcoming
Yes.
tower?
Yes, sir. Yes, sir. Because it is at 72 meters height, right? So
Yeah.
how do you do that? Because whether the Picaro pump will be able to suck the air from that height?
Yeah, exactly. There are special pumps for those things.
Okay.
Yeah, so basically those pumps are designed to work on the tall towers.
Okay.
So those pumps will suck the air and then this air will pass to the sequencer, and then the sequencer will push this air to the instrument.
Okay. Okay. Thank
So,
you.
but before that, the air will go to some dryer.
Oh, yeah.
Yeah, so that air will be dried, and then we'll have moisture dryer and everything, moisture remover, yeah, tap and everything. So it is very well designed.
Okay. Okay.
Yeah, so that is taken care.
Okay. Thank you.
Otherwise, Picaro pump cannot
Yeah.
suck the air.
Yeah, that's what I was worried. You know, 72.
No special pumps, yeah, special pumps are there. Maybe you are welcome to visit sometime in Bhopal, maybe after 2-3 months.
Sure,
So
sir. Sure, sir.
then you can see the setup there.
Sure, sir. Thank you.
Yeah.
So there is a comment by Praveer. Very nice analysis of the power plant emission data. We can see the increase in the baseline emissions first could be of months and later months of 2020.
and there was the lockdown dip.
Yeah. Yeah. Exactly. Yeah, this is comment, I guess. No question.
Yeah, this is comment.
Yeah, that's common point is that the Indian emission increasing that you can see there.
Yeah, yeah. Indian emission, exactly. It's kind of compensated basically by October, November.
Yeah.
Actually, we had a paper here that made initiated by Avid. Probably you could have seen that results.
Yeah, that was a very nice paper. Yeah.
Yes. So Chaitanya posed another question. Good demonstration of emission reduction during COVID-19 on CO2 mole fractions. Yet it was a temporary short-term reduction. Just a comment. Prasenjit ask one question. Do you have simultaneous data using Picaro and flux measurement?
We have for some time, yes. No, actually at Srinagar we did not have Flask, but same time we have data at IITM campus, not exactly same co-located.
That is not published yet, right?
Yeah, this is not published yet.
So Ankit Saraj asked, do you have any published data of 13C along with concentration of CO2 from Picaro and Srinagar?
That Dada, you can reply.
No, actually we do not have isotopic data from Srinagar. We have published one other than what Jogesh is doing flux measurements. We have also published one paper using not Picaro but LGR analyzer. But that analyzer does not measure delta 13C. So far we do not have any isotopic data measurements in Maharashtra. I mean in Srinagar or Pune.
Yeah, we will do soon by this, na? By our Picaro, isotope Picaro.
But recently we have published one paper that using we used Picaro as a campaign mode in Kaziranga where we have a flux tower, but that is very short data, only 1.5 day. So there we have both Picaro, I mean not flux data, but this is with Lycor, using Lycor, that is flux data, and then isotopic analysis was carried out to have another constraint in partitioning the fluxes.
Yeah, so correct.
This paper is published in Arts and Space Science in this early this year.
Yeah, so that will be really great because if we have all co-located, like all eddy coherence, everything is same, like we are bringing in Bhopal, that those data will be really very valuable.
So I don't see any other questions.
Yeah, I have a question, Yogesh. The methane aircraft profiles, we did not publish the data yet. That one.
We are in process. We are writing that.
Process. Okay.
We are writing. Maybe soon we will just.
We will. Okay. Yeah. Thank you. Yeah.
Okay. So
there is a hands. Mihir, you have any question?
I think Mihir cannot speak, but I think he already asked the question in the chat.
Okay.
Okay, so I think Supriyoji, thank you very much for chairing both the talk today in the afternoon hours. And that comes to the end of all plenary and keynote talks of the workshop. And so now next what we have remaining is the panel discussion and training.
After 5 I'm in a meeting actually, so can I call you back? Is that okay?
Okay. So panel discussion and training, but the issue is unfortunately our panel, training, hands-on training people, they have some COVID issues. 4 of them got COVID and one of our instructor also affected. So they want to postpone that. So we are planning now to take that hands-on training sometime in next week possible, because all the people are in our contact. It's just an online session, so we can dedicate half a day session extending hands-on little more detail. So we'll separately have it, and the server participants can remain here and be part of the panel discussion, and we will conclude the workshop after the panel discussion. So you can also express your comments or concerns or some good messages, criticism messages, all you can share here. So it's good that you are also here. If you have any comments, you please type in the chat box. Panel members are already in the panel. Others can type or raise a hand. We'll attend to you. Okay, so let me take forward the remaining part of the panel discussion with a small recap from what we have discussed yesterday. Unfortunately, many members could not remain in the panel discussion yesterday due to various reasons. So let me give a quick overview. We started discussing on the modeling aspects from the Indian perspective. And there are three questions we addressed, few questions we addressed, such as what are the methodologies in practice in inverse modeling of GHGs in India. So we identified 4 groups are actively involved as of now in the inverse modeling. Whether it's an Eulerian modeling or Lagrangian modeling, regional modeling, global modeling. So we had a good overview and get to know each other. And then we discussed a few challenges faced in the regional inverse modeling in India. And one of them was the lack of quality observation. So we have discussed about that, how to improve the quality of observation, especially observation containing representativity for the inverse problems. I mean, large for regional footprint, etc. We discussed. And yesterday we discussed about how to calculate the background concentration in the trajectory model. So there were recommendation to use either carbon tracker, but then CG said is using the PES enhancement territory and pick up a background from there and then integrate invert to get the background. Then consistency of the Sinagat data, why the model able to not capture. So that we discussed extensively yesterday. Fluxes are to blame partially, terrain another thing, etc. we discussed. So I'm going to write this in the white paper. By the way, first 2 days of panel discussion already written down. We are internally communicating with the LOC members. Once LOC member clear it, it will come to the scientific steering committee. And then we discussed more efforts on the characterize the data, especially if Sinagat data, how we can improve, suppose removing some local influences, especially the outlier rejection and the wind dependent rejection yesterday, etc. yesterday discussed. Then there was one recommendation that we may have to consider the community inversion framework adapted from France, for example. That was one recommendation. That was a reply to the question, what are the various methodologies that we are not aware of, where the world is upfront but we are lacking. So some discussion happened, and so we have noted those points down. Then there was also discussion what if we go ahead with a megacity type of program in India. But Shamil commented, but that itself is not a very successful program. Even after 10 years of efforts from the US, they could not achieve a very good success in it. So that was a very good point we taken down from this panel discussion yesterday. Now they were also discussing we have to look up the modeling. I mean, WMO IGCS working on urban scale modeling setup. We need to have a look at those documents to understand if at all we going ahead with such very fine scale inversion efforts. Then more focused training, that was an answer for the lack of resource and manpower development. Many concerns came. More focused training on inverse modeling is required, much more hands-on. Unfortunately, we could not complete the hands-on today, but they are still saying not for a 2 hour, but rather for a few days of training may be good. That was commented yesterday. We taken a note of that. And then going ahead with developing converting some of the weather prediction model into carbon transport model, so that we can also go up with the technological advancement. That's also noted it down. Now frequent workshops and meeting of inter-comparison among the carbon communities in India, that was also discussed. That means we may have conduct something like a transcom type of meeting for Indian carbon cycle people come together and inter-compare their flux estimates and concentration modeling and inverse modeling and observations, etc. So that type of thing can be planned in future. We have a good large community now, sufficient number in the community, so we can think of such a inter-comparison efforts. So that's the point we left yesterday, and we will continue from for today for the remaining 2 questions to address. And before that, yesterday Prabir was in there, and some other members are also left, mostly due to technical problem. There was some lag in the connectivity. So if you have any points to convey to this panel among these red colored points here, you can give that, and then we will move on to today's panel discussion topic.
Yeah, if I may start, but I think what you have already discussed, I think is very good because it's very comprehensive list. I don't think I have anything to add there. I just agree with you. Good job.
Okay, Prabir, thank you very much. So yeah, so the next question we're discussing today, we don't take much of your time because we already crossed 1 hour with the extra talk we added in the afternoon.
Just one point. Yes. I would like to just mention that in order to have, because this has been repeatedly discussed about lack of high quality observation, and that requires training. And I think that young people who are there right now added to the community, they should definitely be encouraged to take training from places which produce high quality observations. And there should be some initiative which should be taken by the community to give them the exposures, like the way we are trying to do workshop like this. So they should be trained in kind of a state of art labs around the world, and which should be kind of initiative taken by the community as such to get a reliable data which we can bank on. So I will definitely prefer that young people who are coming to the community should get exposures in standard labs which are around the world. And many of these speakers who gave a talk, they come from those labs, and maybe they should facilitate that in order to make it happen.
Yeah, well taken that point. I have noted it down. Definitely it will be part of the recommendation we are writing. But yesterday I had a question to you, but you left early, I guess. The question was, do you have any understanding on the soil carbon properties of the Western Ghats? And or also as well as the respiration component, autotrophic as well as heterotrophic from the Western Ghats region. This was our question.
Yes, see, I was mentioning that privately with Supriyo, that we did some experiment talking about how the soil respiration varies seasonally, putting our strength to the soil environment. But this was not exactly the Western Ghats, but it is the regions where we are right now. But it varies drastically, and it goes with a large amount of microbial community which thrives in those environments. And this microbial communities, they do vary between place to place, and there is a lot of unknown parameters which need to be addressed before we can even think of interpreting those data, because finally it lands up into getting certain methane being converted to CO2, which we can actually address that how much is getting converted through process of oxidation. So, but yeah, so this data are not been published. This is part of students' project, which we are able to get some information about variability of soil respiration through time. But there can be concentrated effort in this direction if some projects be funded or something can be done together.
Okay, yeah, thank you very much. Okay, so now we will move on to today's points, such as first point is availability of preparing prior fluxes and inventories from India for regional greenhouse gas inversions. So question is open. Members may now start. Yogesh, please help them if they are raising hand or want to speak, because I'm not seeing the members team.
Yeah.
So maybe begin with, I can start saying what we mean by here is that the prior fluxes is always criticized. Say it be CO2 or methane, because methane we saw that some of the inversions suggest Edgar is overestimated. And if you look at the say the carbon, as for example, the Casa fluxus is very mild. VPRM is giving high values, and so that is one point. And second is the inventories from India itself is not readily available to a larger community like this. That this is one of the area of concern. I mean, this is just some ideas how to start the discussion on that point. Yeah, thank you.
So I think
please.
I think it will be very difficult to have an ideal prior fluxes, and the concept means yes, if you have an ideal perfect prior flux, it's very good for our modeling. And nowadays I'm experiencing that the methane and N2O is very good, and we just worked on a manuscript by Naveen, and we actually have tried two very contrasting. If you want, I can actually show one slide, or something.
Yeah, why not? Yeah, sure.
Figure from that. Just let me show one figure from there. So having a perfect flux is not an idea when you do the inverse modeling. Sometimes, for methane and CO2, we really have a very good one. So, and we already have 2 papers on CO2 and methane published, so we can easily see all the information. But the CO2 is very, very difficult to get ideal flux. And so let me go to the figure. I wanted to just flash here. Yeah, like this one. So you can see the PDF, right?
Yeah, we see that.
You can see the figure, right? Yeah. So what we are doing here is we are doing 2 inversions, 2 different family of inversions. Then let's say just look at the land one, and so this is our like a CASA flux, which is like a annually zero balanced and no internal variability. And the gray line below is that coming from visit flux. So one is like a neutral, no sink on the land, and another one is like a heavy, strong sink on land, because some of the DGVMs do that kind of work, and it happens because they don't include fires and they do not do something and all sorts of things. Anyway, so by starting from 2 different points, our inverse model can actually produce this, at least the IAV and the fluxes pretty well. And this is the challenge, and this is what I think the inverse model is supposed to do. And this is achievable only when you have a good quality, sustained, and regular interval data. I think that's what we should aim to get. If you get a perfectly right model, I think that is very difficult for CO2 because its system is so dynamic. Your agricultural practices are changing. Different year you have a different agriculture. People do a rotational crop. The IOD, all the thing, ENSO, and all the local information, everything.